Among those who consume, the quantity of consumption varies from individual to individual. So we ideally, when you talk about price elasticities, one should be able to talk about price elasticity of participation and the price elasticity of the quantity of consumption. So we would like to ideally distinguish these two, and it is also helpful for policy purposes. So because the Deaton's model did not provide an elasticity of participation, we are now discussing an alternative model which gives both elasticities of participation as well as elasticity of consumption. So obviously these are totally different approaches. The only common factor between both the approaches is that both are using the household expenditure data to estimate these elasticities. So if you find elasticity numbers which are similar in both the analysis, they are not comparable, of course. They can be just accidents, or you'll be lucky if you find similar numbers from Deaton's analysis and this particular analysis. So with that introduction, let me go on into the presentation. So as I already mentioned, we have what is called a prevalence elasticity, which is loosely defined as the proportionate change in prevalence of smoking as a result of a given proportionate change in the price of cigarette. So it is also called a participation elasticity or a propensity of smoking, or it is also called an elasticity on the extensive margin. We also have a conditional elasticity, something similar to what Deaton's model gave you, and that was the proportionate change in the number of cigarettes smoked as a result of a given proportionate change in the price of cigarette. This is the conventional price elasticity that we are familiar with, whereas prevalence elasticity is not something that we regularly see. The conditional elasticity is also called an intensity elasticity or the elasticity on the intensive margin. Roughly in the literature, there are literature on both these elasticities from different countries around the world, and many of those literature sort of converges on the fact that these elasticities are roughly half-half. For example, let's say the total elasticity is say 0.8, the prevalence elasticity will be somewhere around 0.4, and the conditional elasticity is around 0.4. It's roughly 50-50. Well, of course, there can be some differences, but this has been what the literature seen so far. Modeling smoking outcomes. So, as I already mentioned in my introduction, many outcomes, including that of smoking or tobacco use, have two fundamental statistical properties. One, let's say Y is the outcome that you're talking about. YI, the I indicates the individual here. So YI is greater than or equal to 0 for a set of individuals, but YJ again is for an individual is equal to 0 for another set of individuals. So if you look at a survey, a proportion of individuals in the survey will have 0 outcomes or 0 consumption. In this case, it is smoking. Let's say 0 smoking for a number of individuals in the survey. There will be positive smoking for another set of individuals in the survey. So clearly, this a variable on smoking, for example, it's the distribution of the smoking variable. The Y here, Y is the smoking variable here. That distribution is not a continuous it's not a strictly continuous distribution. It is not a strictly bimodal distribution either. So you have a discrete part and a continuous part. So it is something like a mixed sort of a distribution here. So we have to model, we have to fit a more proper model to explain or to be able to predict outcomes when you're dealing with these kind of outcome variables. So one thing to note here is that we never get negative values here. So we have either zeros or positive values. So there is a significant number of 0 outcome in this particular variable, in the smoking variable especially. So because you know that the smoking prevalence is below 50% or 40% or even 30%, below 30% in most countries. In fact, the global smoking prevalence is only around 21% according to WHO. So you will see that, let's say, in your country, your smoking prevalence is only 20%. So typically, when you look at the household or individual survey on smoking, you would see that almost 80% of the distribution of smoking variable will have zero values in it. So obviously, if you leave out all those zeros when you estimate any econometric model, you are essentially leaving out a large number of observations from your analysis, and you don't want to do that, right? So there are different strategies to model these kind of outcome variables. When if you look at read the econometric literature, there's so many different models out there which are specifically made for modeling these kind of outcome variables. But I'm not going into the details of all. You can pick up the textbooks and see those. My objective today is to discuss a certain specific model that is usually used in the literature to model smoking behavior or smoking outcomes which are of this particular nature that I discussed. So there have been several econometric strategies to model outcome variables with a large number of zeros and positive magnitudes as a function of a set of exogenous covariates. So one model is, of course, an Euler's ordinary least square regression, which is a very conventional way of modeling. So you basically fit an Euler's model on the outcome variable y, which is the cigarette consumption. But obviously, in this kind of a model, because the y is zero for a large number of non-participants or people who are not consuming cigarettes or smoking, they will all be zeros. So the model will entirely ignore those zero observations completely from the analysis. And also, this dependent variable can generate biased parameters if they are not normally distributed. So many times these consumption variables are not normally distributed, and this is especially the case with the household survey data. And there are a lot of reasons why households survey produces not really normal outcome variables on a variety of variables that you see. And an Euler's model can also predict negative outcomes. You know, once you fit the model and you make a prediction, it can give you a negative prediction, negative consumption or negative smoking, which is unrealistic, because we know that the smoking cannot be either only zero or positive. It cannot go negative. So these kind of problems are there while using Euler's model to fit to explain outcomes of this nature. And then people conventionally have also resorted to using log transformation of the y variable here. So, for example, the y variable, because it is normal, it's not normally distributed, or because it has heteroscedastic tendencies, people take the log of that. So you transform the y variable into a logarithmic form. So the expectation is that a good log consumption is normally distributed. Consumption which is in raw scale, which is y, is usually not normally distributed, but once it is logged, the chances are that it is normally distributed, but it is not always the case, of course, you know it. So the predicted consumption is affected by retransformation bias in such cases. I'm going to talk about that soon. Also, another problem here is that you can't take the log of zeros. So again, zeros are ignored in this particular model also. And it also assumes that variance of errors is constant, but you know, obviously logging of a variable does not guarantee that the errors that you get from the regression model are constant. So there's no guarantee on that. Okay. So I forgot to mention that I'm actually going to discuss the theoretical model in bit of a detail And then my idea is to, once I finish with the theoretical model, and show you what it is and what we're going to estimate. I intend to show you or walk you through the estimation process with the help of Stata, and I have already made my Stata do file ready, and I have the database with me which was sent by Marco. It is a data from Belgrade. So I'll be running these models with the help of Stata, and you will be able to see the results on screen. Depending on when I'm going to be able to finish this theoretical discussion, and depending on how the time permits, we can decide whether or not to do this practical session today, or maybe we want to do it sometime later, or we take some break in between and then continue the practical session afterwards. So we can come to that once this presentation, this part is over. The two-part model, so I already discussed how people have modeled these kind of outcomes with traditional Eulers and Eulers with the log transformation, and now a two-part model is a certain way of modeling this outcome in a way that we don't lose any of the zero consumers, like those who don't consume at all. So essentially, a two-part model splits the consumption into two parts, as the name suggests. So we have the first part, we look at the probability of any consumption, basically the probability of participation. What is the chance that you are a smoker? So it uses the entire sample of the survey. Suppose you are dealing with a household survey, the full sample is included in this first part of the analysis. So, and the probability of observing a positive versus zero outcome is what is modeled in the first part. And obviously, it can be estimated with the help of probit or logit. You all are familiar with the probit and logit model. They're very common in the literature, if you see. And second part is actually looking at the level of consumption, or it's looking at the consumption conditional on the fact that yi is greater than zero. So conditional on the fact that somebody has chosen to smoke, you are trying to model the level of smoking or the quantity of consumption or quantity of the number of cigarettes that is smoked. So obviously the second part only uses a subsample, right? So because the zero consumers or the non-consumers are exempted from this analysis in the second part. You can fit an appropriate regression model for the positive outcomes conditional on the positive purchase. So in the literature, you will see that people have used Eulers or log transformed y variable or GLM, which is generalized linear models. So these are some of the standard models used to model the second part of the two-part model. So when you do the predictions after you complete the estimation of two-part model, the predictions are usually made using the entire sample, the sample of zeros and non-zeros. So the idea of a two-part model is that it allows for the independence between the decision to smoke and the decisions of how much to smoke. There is an independence that is assumed. So obviously these two steps are done independent of each other. So you first estimate the first part as a probit or logit regression, and the second part conditional on the fact that you're smoking, which means you are selecting the subsample and fitting the Eulers or GLM on the second part independently. So these are two independent estimations. So we would like to predict the total expected smoking, say E of y given x, a set of covariates. X is a set of covariates that we are looking at, right, as a function of a set of covariates. The 2PM or the two-part model takes advantage of the basic rule of probability here, because the E of y given x, so the expectation of y given x is modeled as the probability of y greater than 0 multiplied by the expectation of y conditional on the fact that y is greater than 0. So they are independent. That is why we are able to multiply it like that. The total expected smoking is here equal to the probability of smoking multiplied by the expected quantity of smoking for those who smoke. So that is how, when we make the prediction, right? So when we predict the quantity of smoking from after the two-part model, the prediction is done like this. You multiply with the probability expected, the predicted probability from the first part, multiply with the expected mean or the mean quantity of consumption that is estimated from the second part. So multiply one with the other, you actually get the actual expected quantity of consumption or quantity of number of cigarettes smoked. So in other words, the 2PM or the two-part model assumes in the part 1, the probability of yi greater than 0 given a set of covariates x is governed by a parametric binary probability model like logit or probit. In part 2, as I already said, the expectation of yi given or conditional on the fact that yi is greater than 0 given a set of covariates x is modeled as a linear function of the covariates x, and it is estimated usually with the help of OLS or the GLM. It is also the case that in the literature, a log transformation is commonly used in practice to model the second part, wherein the y is transformed into a logarithmic form. That is, you take the log of y. Log y is what is being fitted in the second part of the model. So there is a prediction bias in the 2PM model, the two-part model, especially when we use this log transformation. And why I'm talking about this prediction bias is because of the fact that there is a large literature out there which has estimated this two-part model using log transformation of the dependent variable in the second part. And we don't want that mistake continuing. Only in the last couple of years, the literature has now begun to acknowledge the kind of mistake that was happening while estimating the second part with the log of the dependent variable. So this is the reason why I want to briefly discuss the prediction bias in a two-part model. And the prediction bias is something that happens when a log transformed second part is used instead of GLM or some other method. So for example, the predicted cigarette consumption, as I already discussed, is the total predicted cigarette consumption is the expected value of y given x is obviously a multiplication of probability of positive consumption into the expectation of the y given y greater than 0. If the second part of the model was simply y is equal to x beta plus epsilon, see that is the second part of the model, which is y greater than 0, right? So suppose the second part of the model was simply y is equal to x beta plus epsilon. It is estimated with OLS, and then you take an expectation of that, it gives you expectation of y given x as xb, right? Because the expectation of e gets cancelled. The continuous distribution of y is often skewed to the right and can have non-constant variance. And this is especially the case of y that you usually get from household expenditure surveys. So in the literature, as I already discussed, a log transformation of y was done. It is a commonly used solution to stabilize the non-constant error variance and or to more nearly satisfy normality. So the assumption is that once you transform the y into a logarithmic form, you're able to address the non-normality issues, and you're also able to account for the heteroscedasticity in the error terms. So the assumption is that you have a sort of a constant error variance once it is log transformed. But obviously that assumption is not right most of the time, especially when you're dealing with healthcare data or consumption data that you typically get from household expenditure surveys. So because the y is log transformed, for you to be able to make any predictions, you have to retransform the model after doing the estimation, right? The retransformation after the Euler's equation of L and y is needed to obtain a consistent estimate of the mean response of y, because we want to do the prediction on y and not on ln y, right? So because it is ln y that is estimated, once the model is estimated, you have to retransform it back to its raw scale y so that you can make meaningful predictions. A typical log linear regression for the second part of the 2PM model looks like this. The log of y is equal to x beta plus epsilon for y greater than 0. This is our typical log linear regression model for the second part of the 2PM model, right? The corresponding demand function in its original raw scale would have the exponential relationship, which is y is equal to e raised to xb into e raised to epsilon, right? You transform the log back to its raw scale. So the function in the first line here, ln y, you convert it back to the raw scale y. The right hand side become e raised to xb into e raised to epsilon. Most studies, however, neglected to include the last error term while going back to the original scale for prediction purposes. So most of the previous studies have ignored the e raised to epsilon part while retransforming the ln y back to the y. So these studies had e of y given x simply taken as e raised to x beta, when the correct expectation would have been e raised to x beta into e raised to expectation of e raised to epsilon, right? So that part which is expectation of e raised to epsilon has been omitted in many of the previous studies. That is the prediction bias we are talking about. A prediction based on a naive transformation which does not take into account this error retransformation, which is the transformation of this error term also back to the raw scale, which is expectation of e raised to epsilon. The retransformations that omitted or ignored this particular component has in effect biased the estimated results. So the log transformed equation consistently estimates b, which is necessary but not sufficient for accurate prediction because it is biased by the element e raised to, expectation of e raised to epsilon. Because you are not fitting your model to expectation of y given y greater than 0, but to expectation of ln y given y greater than 0, a correction for this bias must be made. So there is a literature which shows that you have to correct for the fact that this e raised to expectation of e raised to epsilon has been omitted. So the error retransformation expectation of e raised to epsilon is often not constant and is heteroscedastic in the covariates that you're looking at. So if the log disturbances are normally distributed, suppose you do the log linear model with the log y on the left hand side and the linear terms on the right hand side, and if it so happens that your disturbances are normally distributed, then you are good because you have the normally distributed disturbances with the constant variance sigma square. The retransformation expectation of e raised to epsilon can be easily constructed. You can construct it as e raised to sigma square by 2, and the sigma square can be estimated using the mean square of the error from the log transformed regression. So this is pretty straightforward. But if the error distribution is unknown, there is this particular proposal in the literature by Duan. It is called Duan smearing estimator that is used, and the Duan smearing estimator is estimated as the average of the exponentiated residuals. So you have the exponentiated residuals which are estimated from the log regression, and you take an average of that. So the average of the exponentiated residuals is used as a smearing factor to adjust for the bias, and this is called a Duan's smearing correction. I'll actually show how these things are done in Stata step by step, so you exactly know what is happening. But if the errors are heteroscedastic, this particular smearing suggested by Duan will not work. You have to use a heteroscedastic version of this smearing estimator to be used. But that is very involving, and heteroscedastic retransformation can be intractable, especially when heteroscedasticity is in a continuous covariate, like for example price. Price is a continuous covariate, and if the heteroscedasticity happens on price variable, so this sort of retransformation can become intractable. And this is the reason why most of the previous studies did not bother with this this Duvan's smearing correction or Duvan's smearing. So they've all ignored this. So this is the prediction bias in 2PM model that existed till few years back in many of the studies. I just highlighted it here because this is very much part of the literature on 2PM model, two-part model. But having realized that these sort of problems exist, we need to have a way of doing without the need for this smearing, Duvan smearing or something like that. So the model that we're going to discuss today, which is GLM or generalized linear models, will do away with the need for smearing like this, and and make the estimation of expectation of y straightforward. But of course, if you find that the log y or the log linear model for the second part does not have any heteroscedasticity, then doing a two-part model with the first part with logit or probit or second part with Euler's is okay, or in fact it is better, because Euler's coefficients are always the best unbiased estimator. So Euler's is actually best if the error variance are constant, or if the variance is constant for the log Euler's model in the second part. But we know from experience that more often than not, the error variance are heteroscedastic, or errors are not normally distributed when we are dealing with the household surveys, and that is pretty much the norm. So we know that it is safe not to use this in the first place. So this was proposed in 2001 by Manning and Mulle, the GLM model for the second part of the two-part model. The generalized linear model was proposed as a solution to address or to avoid the need for using smearing while estimating the second part of the two-part model. So the GLM is again a standard linear model, which most of you are probably familiar with. But just for the sake of those who are not heard about it, I'm just going to give you a very brief introduction into about the GLM. The GLM model generally can be written as a generalized linear model of y with covariates x, right? So you see g as a function of e of y is equal to x beta, where y is distributed as a distribution f. So where the g of y, so the g of e of y, basically that function, whatever that takes, is called a link function, which links the y with the distribution. It links the e of y and the x beta. What is the function that links the e of y on the left hand side and the x beta on the right hand side? That is a link function. And the distribution of the y itself, that is the f. That f is the distribution of the y, and so depending on the particular family of distribution that y takes, and depending on the nature of the link function, the GLM model varies. So the good thing about the GLM model is that it does not require normality or homoscedasticity to model the second part of this two-part model. The GLM, unlike Euler's, uses a maximum likelihood estimation method by default. It also has iterated least square estimation. You can specify if you need, but by default it uses a maximum likelihood estimation method. The Euler's estimator on the ln(y) estimates the expectation of ln(y) given x, and it requires retransformation to log of expectation of y given x. On the other hand, GLM would estimate the log of expectation of y given x and consequently E of y given x directly and avoids the need to retransform. So because the GLM would estimate, especially when you're using a log link function in the GLM, it will straight away estimate the log of E of yx. So as a result, you don't need to retransform it back. If y is distributed as a Gaussian or normal distribution and g function is an identity function, we have a standard linear regression. For example, your E of y is equal to x beta, where y is distributed as a normal or Gaussian distribution, and the functional form here, that is functional link form that is used, link function that is used to explain the relationship between E of y and x beta is an identity function. So this is what you typically get in an Euler's model. So for example, the idea of this is that if you do a GLM model with the normal distribution and identity link, the result will be identical to an Euler's regression model. Similarly, if the y distribution is binomial and the link function is a logit function, we have a standard logit regression. So, so the GLM command with a logit function and a binomial family, a distribution family, will give the results identical to a standard logit command in Stata. Okay. So there is an array of distribution families and link functions to choose from to fit the GLS model. You can think about any different type of distributions out there. You just need to specify a family of distribution, and you need to specify a function for the link. So that is all it matters. So once you specify, depending on the type of link function and the distribution family that you specify, the GLM fits the models differently. In particular, in the two-part model, if you look at respectful literature in the last couple of years, it has been proposed that a family gamma or a gamma distribution and a log link as a link function are best when you model these health related or consumption related or kind of variables. So if you look at the healthcare literature, or if you look at the literature on consumption, demand, modeling of demand functions or modeling of cost functions, etc., they all use GLM model with gamma as family and log link as the log function as the link to model. So, and this has been proposed by Bellotti et al. In 2015 and Manning et al. In 2005. So there is now a consensus that a GLM with the gamma and log link is pretty much as accepted standard while fitting the second part of the two-part model. So when the link function is natural log, then the beta represents percentage change in y for a unit change in x. So remember here our link function is in log. So when you do the prediction after the estimation, we have to keep this in mind. So this I will show when I do the exercise in Stata. These are the set of family and link options available to choose from in Stata. As you can see, there is a number of link functions out there: identity link, log link, logit link, probit link, odds and power and negative binomial and whatnot. And family, you have 5-6 different families to choose from: Gaussian normal family, inverse Gaussian, binomial distribution, Poisson distribution, negative binomial distribution, gamma distribution. I'm not a statistician, so I wouldn't be able to tell you the exact difference between all these distributions. So some of the statisticians listening can contribute later if you if you like. All right. So for Stata also assume a certain default link for each family, and for family Gaussian, an identity link is assumed by default. Similarly, for family gamma, a power link of -1 power is assumed by default. But we can specify, but Stata only allows you to specify certain links with certain families. You can't look at the permutation and combination of all families and links. That is not possible. See, for example, if you are using a gamma distribution, if you choose the gamma as the family distribution, you can only choose a link function as identity or log or power. That's it. Only 3 link functions you are able to choose if you choose the gamma distribution. So thankfully for our purposes, a family gamma and log link function is pretty much enough for our purposes. Now, a GLM with the family gamma and link log, a bit more detail on that. The goal is to estimate the mean function E of y given x. That is our goal. And for this, we specify a distribution f for y that reflects its main variance relationship. So that is the distribution which the gamma distribution is the one that we are saying here will reflect the mean variance relationship, and a link function g dot between linear index x beta and mean mu. These are the 2 things we need to specify. A gamma distribution has a variance function that is proportional to the square of the mean function. So for a gamma distribution, the variance function, which is v of y given x, is proportional to the mean function, which is expectation of y given x square, the square of the mean function. So the log ln E of y given x is equal to x beta, or in other words, expectation of y given x you can see as exponential of x prime b. GLM family test. So in Stata, in the theory, there are some tests to do to test whether a certain family rightly fits the model or not. So when you're fitting the GLM model, you can see which family is more appropriate for the particular distribution in hand. So if you have the distribution of smoking as a variable, y variable is the distribution of smoking. So we can test actually if the gamma distribution is indeed the right distribution to fit for this model. And suppose if the test tells you no, gamma is not the right distribution, there's some other distribution that you have to use. Obviously, it is not necessary that we have to use the gamma. We can use any other distribution as the test reveals. So modified Park test is a test that is commonly used in the literature to test the particular family distribution that should be used in a GLM model. The GLM does not assume a constant variance and instead assumes there is a function that explains the relationship between variance and mean. To choose the most appropriate exponential probability distribution, one must specify a suitable variance function. So basically, it is a variance function that we are trying to choose through this modified Park test. A modified Park test is used to choose the most appropriate variance function and recommends family given a particular link function. So for a given link function, the modified Park test will recommend a distribution family to fit the GLM model. A general relationship between the variance and the mean for a GLM can be described as variance of y given x is equal to alpha into expectation of y given x to the power lambda. But for a baseline GLM model with gamma distribution and log link function, the above relationship can be defined as log of y minus y hat square is equal to log of alpha plus lambda into log of y hat. So this is how the last line here on the slide is how gamma distribution the baseline gamma distribution and the variance the relationship between the variance and mean function is defined. So once you have this, you can actually estimate a model. You can actually use the GLM itself to estimate this particular model. For example, here use the GLM to estimate the model log y minus y hat square is equal to ln alpha plus lambda ln y hat plus epsilon. You estimate this model. I mean, this model can be estimated using either Euler's or GLM, but the literature usually recommends that you estimate the same thing again with the GLM only. So once it is estimated, the coefficient associated with the log y hat on the right hand side. Here you remember y hat is actually the predicted y's from the GLM regression. We first do a GLM regression, a baseline GLM regression we start doing with gamma as the distribution family and log link as the link function, and then we predict the y hats from that particular GLM estimation, and then do another GLM estimation here in the second stage, defined like this. So we for this GLM estimation, we define a left hand side variable which is log of y minus y hat square, and on the right hand side you have the log y hat, and now the lambda, which is the coefficient on the log y hat on the right hand side, the value of that coefficient lambda will indicate the appropriate distribution. If after the GLM regression you find that this lambda is equal to 0, it tells you that you have a Gaussian distribution and it's a normal distribution with constant variance. If lambda happens to be 1, it indicates that your family of your distribution family for the y variable is Poisson. So you have a variance proportional to the mean in such a distribution. If it is a gamma distribution, then the lambda will take the value 2. So your variance is proportional to the square of the mean here. Unlike Poisson, where it is only proportional to the mean, here the variance is proportional to the square of the mean. And if the lambda takes the value 3, what we have is an inverse Gaussian or Wald distribution for the y variable. There, the variance will be proportional to the cube of the mean. So we basically, obviously, this when you do this GLM estimation, it is not necessary that you exactly end up with a lambda value equal to 0 or lambda value equal to 1 or 2 or 3. You can end up with any integer in between 0 and 1. You can end up with 0.5 or 0.7 or 2.1 or 2.5. All this is possible. So we basically do a statistical testing to see whether lambda is equal to 1, or a test to see whether lambda is equal to 2, if it is statistically significant or not. And if not, we try to choose a lambda value which is closer to the estimated lambda value from this particular regression model. That is what is typically done in the literature. Use the estimates to construct a working variance function and conduct more efficient second round estimation and inference. So suppose we start off with a baseline GLM model with a gamma family and log link function, and this particular modified Park test tells you that your lambda value is 1, then you want to then start your modeling all over again, and then estimate the GLM model with the Poisson family distribution instead of a gamma family distribution. That is the whole idea behind doing this modified Park test. All right. But if the lambda is closer to 2, of course, we can continue with the same gamma distribution that we have assumed to begin with. Now, this is a test for the link function. Remember, the modified Park test was done to choose an optimal or more efficient family distribution for a given link function, right? So now this test here is a box-Cox regression. Is done usually to choose a better link function, right? So we start with a log link for the gamma and log link model earlier, right? So this here this is the standard box cost transformation that many of you have studied in your regular econometric classes, right? So to determine the relationship between x beta and the expectation of y given x, you do a standard box cost transformation of the y variable, that is y raised to the power lambda minus 1 divided by lambda, and you estimate that particular y variable. The transformed box cost transformed y variable, you estimate it on the set of covariates alpha plus x beta plus eta, and you typically use the MLE maximum likelihood estimation method to find out the value of lambda. Once you find out the value of lambda, you can actually define the type of link function. See, for example, the estimated lambda, which is lambda hat from this particular regression, happens to be 0, then we use a log link, in which case our link function will be specified as ln y is equal to x beta plus epsilon. If the lambda value is 0.5, we specify the y as square root. So root y is equal to x beta. That's a square root link. If it is 1, we use an identity link, which is simple y is equal to x beta. And if it's 2, you use a square link. If it's minus 1, use a reciprocal link. So again, please remember this box cost regression. This result can be influenced by outliers and stuff. So again, the convention here in the literature that I've seen is that you don't end up with strictly these zeros and 0.5 and 1, 2, etc. But you most likely end up with a number which is close to any of these numbers shown on the screen. So you tend to take the one that is closer and say that is the link function that is more appropriate. All right. So I hope people don't have any questions so far. Now, what is remaining is basically discussion of some, model diagnostics for our purposes. So we can test for the nonlinearities. Remember, the GLM basically assumes the linear model on the right, the link function. Depending on the link function, we assume, we assume a log link. So obviously, the right-hand side variables are linear. We can test for the nonlinearities and goodness of fit of the model. There are different tests out there in the literature, but I'm only discussing a few select ones which are more commonly used. One is a standard link test, and link test is commonly used as after logit and probit commands, and even ordinary least squares also you can use link test. After the regression, you can simply issue the command link test in Stata. So the link test basically tests whether the coefficients of y hat square is significantly different from 0. So you basically estimate the model and you predict the y hats, take the square of y hats predicted, and then you refit a model on this y hat square and see whether the coefficient associated with the refit of the model on the y hat square is significant or not. If the model is specified correctly, the coefficient associated with the y hat square should have no explanatory power. I'll show how this is done in Stata. And then there is the Pearson correlation test, which is a test. It tests the correlation between prediction error and fitted values. And then you also have what is called a deviance residuals test, which is supposed to be more favorable test of goodness of fit for GLM models. It is defined, the deviance residual is defined as a square root of the contribution to the LR test statistics of a saturated model versus the fitted model. Basically, this is used to assess the choice of variance function. I'll show how again this is done in Stata, so that then you will know exactly how these particular statistics are calculated. And then lastly, we have what is called a modified Hosmer and Lemichaud test. Hosmer and Lemichaud test, the standard test is used mostly after the logit and probit models. but this is not the conventional Hosmer and Lee-Michaud test, but slightly modified version of that. This is to check the fit of the model for any systematic bias. The partition, so ideally to do this Hosmer and Lee-Michaud test, we partition the residuals in the raw scale into equal sized groups. Usually we partition into 10 equal sized groups of residuals and check their distribution in each of these 10 different decile groups, and then test if these residuals are jointly significantly different from zero. So usually the Pearson correlation test and the modified Hosmer Lee-Michaud test gives similar results, but the deviance residual results can be slightly different. And link test only tests for the nonlinearities present in the model, whereas Pearson correlation test, deviance residual test, and this MHL test, they all test for the goodness of fit of the model. And then there is also a COPAS test. It is a test. It tests the model's predictive ability and avoid overfitting. This is a model test to see whether your model is overfitted. It randomly splits a sample into two, that is A and B, two samples, and then test model A's predictive ability by predicting the expected consumption in a sample B using the estimated coefficients based on sample A. So this COPAS test is usually very involved, and this won't be discussed in the Stata, because you have to go through a lot of bootstrapping and stuff. It is not something straightforward, but we will be discussing these other models of goodness of fit, other tests of goodness of fit. So I think the results from these three tests that we mentioned here, by and large, would enable us to make a decision on the model. So I saw a pop-up from Violet. I'm not sure if it just came and went off. So let me see.
Yeah, so I wasn't sure if anyone had any questions, so I just wanted to remind them to. So if they have any questions, they can interrupt. I mean, they can send me or they can raise their hand. So I just wanted to. But just, I mean, I didn't mention, I mentioned in one of the emails to Rivera, but I didn't mention today. I realized that I'm actually recording this webinar, so you will be able to revisit again, see it again at your convenience later on. So if you have any, like if you think, oh my God, I need to take notes or something, don't worry about it.
Yeah. Also, I'll be glad to share the PPT and also the do file that I'm using today for the Stata exercise. I'll share both of them with you. I'll send it to Violetta, and then she will share it to all of you. So you don't really need to take down any notes right now. You just can concentrate on the talk on the screen, right? So are we good? So I'll proceed.
Yeah. I don't see that anyone is.
Okay. All right. So okay. All right. So these are the tests we discussed. Okay, fine with me. Thanks. Okay. All right. So these are the tests that we discussed, and then now in the recent literature, there is also something called an extended estimating equation, also called a power GLM. Instead of the regular GLM that we've been discussing, there's something called a power GLM, which is developed by Basu et al. In 2005. But it is, I see that it is not been very popularized yet. The idea behind it is that it estimates the regression coefficients and the parameters in a flexible Box-Cox link function and a flexible variance function simultaneously. Remember in earlier family test and the link test, we used the Box-Cox for the link test, and we used a modified part test for the family test. But there we saw that it is possible that you end up with the coefficients which are not which are integers, like you end up with a 1.5 or 0.5 for lambda, in which case you do not know exactly whether the number that the lambda returns is not exactly equal to either 0 or 1 or 2, right? So so you don't really know whether it is fully correct to use a gamma distribution, for example. So power GLM, on the other hand, use these exact integer values for both family and link function to estimate the model. But they have developed a special package called PGLM. It's a user-written package in Stata. So those of you who want to explore more, I've given some reading at the end. You can read through, and instead of using the GLM, you're free to use the PGLM. But I see that it's a bit more involving, and you really don't need it, because I still don't see, although this model came out in 2005, even the most recent literature that I've looked at, they all use typically a GLM with log link function and gamma distribution family. So that is that I did not discuss much on this power GLM. Now, some advantages of the GLM. I'm almost concluding this talk here, the theoretical talk. There is no transformation bias when predicting, unlike in a log OLS model, because the link function in GLM allows modeling of the log of mean consumption straight away, that is ln of E of y given x, unlike the log OLS that models the mean of a log consumption, expectation of ln y given x. So it avoids the need to retransform. There's also gains in precision from estimator that matches data generating mechanism. It's consistent even if not the correct family distribution. So even if, let's say, your family distribution is specified slightly incorrectly, still the estimates are consistent. And then the choice of family only affects the efficiency of link function and covariates and the covariates are specified correctly. If the link function and covariates are specified correctly, the choice of family only affects the efficiency and not the consistency. So efficiency may be affected a bit if your family distribution is specified incorrectly, but the estimates are still consistent. It doesn't assume homoscedastic errors. That is again a major advantage, especially working with the household survey data. Something that OLS will have problem with. And the dependent variable can be 0. Obviously here we can have a dependent variable which is 0. I mean, this is true only when working with the two-part model for first and second part, but if you're only working on GLM in the second part alone, so the zeros cannot be part of the model. So I think this dependent variable can be 0 should not be an advantage in this screen. I should take that out. That's an advantage when you are doing the two-part model, including the first and the second part. So I remove that later. And some of the disadvantages, it can suffer substantial precision losses if there is heavy-tailed error terms, that is log scale residuals of high kurtosis above 3, then it can have some precision losses. Obviously, it affects the efficiency of the estimate. If the family is misspecified, that is a failure to closely approximate the variance function, again, it can lead to some precision losses. So these are precision losses that you're talking about when you're going into a prediction after the model estimation. But if you're not interested in predictions, if you're only using the model to estimate consistent parameters, this is not a significant problem. Choosing the correct family and link can be a challenge. Obviously, we have programs like PGLM package here, which takes care of that, but we don't go into that. So that ends my discussion of the theoretical model. Of course, I try to make it as lucid as possible. I don't want to. I mean, I didn't write a lot of equations here because it's sort of an offline presentation. I mean, it will be difficult to interact with a lot of equations on the screen. So I hope the idea behind the model is clear to you. That in a two-part model, we model the consumption of smoking in two different stages. In the first stage, we model the probability of smoking. In the second stage, we model the quantity of smoking given that a person has decided to smoke. So together, although we model them as separate in two different steps, it is also possible to model them in one shot. There is one shot command in Stata to model them in a single shot command. It will give you the results from the first first stage and the second stage together, and will facilitate the prediction for the whole data easier with a single shot command. I will discuss those when I go into the Stata exercise.
So Rijo, I just have one question.
Yeah.
So for the second part of the model, you said that it assumes that the person has decided to smoke. So which means that the price is a determining factor for someone to decide between smoking or not, right?
Yes. So that is what we're interested in right here. We are interested in the estimating the extensive margin. So
right.
So in the first part. So in the first part, when you estimate the probability of smoking, you have a set of right-hand side covariates where price is also one of the covariates. So it is the same set of covariates that you're also modeling in the second part. So you have in the first, the price is a covariate both in the first part as well as the second part. So obviously you can see the effect of price on the probability of smoke in the first part and the effect of price on the quantity of smoking in the second part.
Okay, so I just wanted to kind of clarify this between this and the previous analysis we done, because there we disregarded the households or well, consumers or non-consumers, meaning that those that at the moment do not spend any income on tobacco, but however, that does not mean that the price, for example, was lower, that they will not be smoking. So here you first determine whether the price is a relevant factor for anyone, and then based on that, you then decide whether someone is a consumer or non-consumer, not depending on what they declare in the household expenditure survey.
Correct.
Okay.
So any questions? If you don't have any questions,
I have a question as well. At least from what I'm hearing here, practically this second part of the model is practically the same that we are doing as we have done in Dietland's model. So we are estimating the elasticity on the intensive margin in both cases. So
yes, yes and no. I'll tell you the difference. See, in the Dietland's model, I agree that you're estimating the elasticity only for those households who are consuming tobacco. I agree, that is right. Because your unit value was available only for those who consume or those who spend on tobacco, right? But if you remember, in the Dietland's model, the budget share equation had the entire set of households, those consumers and the non-consumers. Now, it's a different thing whether you choose to include only the consumers in both the budget share and the unit value regression. But ideally, as I had discussed, Dietland's model would like to see in the unit value regression, there will be only consumers, whereas in the budget share regression, you will have both consumers and non-consumers. That's how the ideal setup happens in the Dietland's model. But I believe that some of you, and in fact there's other literature also out there which has used the same consumers for both budget share as well as unit value regression. So if you used only that, I believe in Serbia you used only the same consumers for both the unit value and the budget share regression. So in that respect, this is somewhat similar. I agree.
Okay, and given the fact that actually we face the same problem that we had before, and this is that we don't have prices of cigarettes, and I see that one of the dependent variables that you're using is actually real price of cigarettes. How are we going to overcome this issue? Because we used Dietland's model first because we couldn't have the actual prices.
Yes.
So this is why we needed to go over to unit values. And yes, so my question is actually, how are we going to estimate this?
Yes.
Are we again going to use unit values?
Yes.
Okay.
So I'm going to explain that in the next slide in preparing the data. So what are the compromises that we have to make to run this model on a household survey data?
Okay. Okay. Sorry for jumping ahead.
No problems. So if you are I would actually like to take a 5 minutes break before we start the next session, because next session is basically the practical session, pretty much. Oh no, actually, no. Let me see. Oh no, actually, I can. Let me finish. I'm not going to the Stata yet. I just run through the presentation to show some of the Stata commands. And before I actually open my Stata, I will take a 5 minutes break, if you agree. Yeah. Okay. All right. So preparing the household expenditure survey data. The household expenditure survey data is already you have, and those of you who have estimated the detailed model already have many of these variables lined up. So you have the consumption of cigarettes in the household expenditure survey. You have the expenditure spent on cigarettes, as well as the number of packs of cigarettes consumed in a household. So that is given. So that's well and good. But we don't have the prices of cigarettes. So what we have is unit values. So obviously, unit values are not exactly the same as prices, but you will see in the literature that unit value is used as a proxy for price in many studies. Although they are not perfect, because that is the reason why Deaton came with this beautiful model wherein he corrects for some of the biases in the unit values. But unfortunately, for this particular model, we have to use unit values as proxies for prices. That's the only way to go ahead with this model. And that is the compromise we have to make. And that is the reason why I'm saying that the results that you get here in the second part of this model also cannot be strictly comparable to the results that you get from Deaton's model, which accounts for the fact that unit values are slightly different from the prices, although we saw that the quality elasticities are very negligible. Any questions? I heard some sound. Okay, never mind. So the real prices of cigarettes, we use the unit values from the household expenditure survey. The unit values are essentially derived using the expenditure on cigarette as well as the consumption quantity. So expenditure by quantity gives you the unit values. So those are the proxies for prices. In fact, there is many literature out there which uses unit value as a proxy for prices, although the Deaton and some of the subsequent literature says that it is really not a perfect proxy. Income of the person or the household is again another covariate that we use, and that also is available in almost every household expenditure surveys. And then we would like to use the demographic and socioeconomic characteristics, for example, household composition in terms of the ratio of males and females, or ratio of adults to kids, or the household size, or or those are the kind of demographic and socio-economic characteristics, or whether the household belongs to a particular ethnic group, or whether what kind of income group they belong to. These are all different characteristics that you can use. They are all potentially determinants of consumption of tobacco. So we need to be able to control for all those variables on the right-hand side, while our particular interest will be focused on the price variable and also income variable if available. And then education attainment of a household, because we are dealing with, ideally when we run this kind of models, we would like to have an individual level data which gives information at the individual level. But since we are working, in the literature so far, let me admit to you that all the two-part models that I have seen in the literature, they've all estimated using GATS or some other individual level data. Global Adult Tobacco Survey is what I'm talking about. So it gives consumption of cigarettes at the individual level. But whereas we don't have GATS data at our disposal, I believe. Many countries don't have GATS data. But what we have is only household expenditure survey data. So what I'm proposing here, let me admit that it is the first time that this two-part model is applied on a household expenditure survey. So you see, we have households as the basic unit of analysis here. So obviously, a lot of demographic and socioeconomic characteristics we have to build in the data for a household as a whole. So household is a single unit of analysis here. So that is why when we talk about educational attainment, we might talk about either the educational attainment of the household head and consider that as the educational attainment for the whole household, or we can come up with an average education for the entire households, basically by simply averaging the total years of education received by every member of the household. So we can say, yeah, a certain household has an set average education of so many years. So these are the ways in which we have to build household level characteristics from data that are usually available at the individual level. So in all the household expenditure survey data, this kind of demographic and socio-economic characteristics are available at the individual level, and we have to aggregate them to the household level. And why we need to aggregate? Because the consumption is only available at the household level. It is not available at the individual level, and that is the reason we need to aggregate. Also, the income is usually in a household survey not available per person, but it is only available at the household level. So some of the important variables that we need for the analysis, like consumption, price, and income, they're all available only at the household level. So we have to depend on household as a unit of analysis instead of a person. And then we can use regional dummy variables to represent different regions in the country. If you see this, if you think that these regions are fundamentally different from each other. And then in the literature on two-part model have used some other variables like exposure to cigarette advertising, the anti-smoking sentiments prevailing in different regions, or access restrictions, or restrictions to the media, etc. on tobacco products, or how children or youth are restricted from accessing tobacco products in different areas. Like there are some places where you can't purchase cigarettes from shops near to the schools, or shops near to the schools are banned from selling cigarettes, for example. Or there are countries where which prohibits children below certain age from purchasing cigarettes. So these are the access restrictions, and sometimes it's possible that within a country these kind of restrictions can differ across regions, and smoking sentiments or the anti-smoking sentiments can differ across regions in a country. So these are some of the variables which are good to control for while estimating these models. And one other thing here to note is the price here. Let me come back to the price again. So I told you that we are using the unit values as price. But remember, in the first part of the model, we are modeling zero consumption or consumption or not consumption, right? And on the right-hand side, we have a set of covariates including prices, where price here is obviously the proxy. The unit value is used as the proxy for price here. So we don't have the unit value for households who are not consuming. So when we estimate the first part of the model, on the left-hand side you have the probability of consumption, which is the first part of the model. I told you that we are using the entire sample of consumers and non-consumers. So on the left-hand side, your Y variable will be a dummy variable for smoking, which takes the value 1 and 0 for those who smoke and don't smoke. But on the right-hand side, your price variable and all these other variables. But obviously, price variable or the unit value, which is used as a proxy, is only available for those households who report consumption. So what do you do with those households who do not consume? So what we have done here is we have aggregated the prices of all households within each PSUs or within each um, uh, you know the PSU is the primary sampling unit in a household expenditure, in a household survey. PSU is the primary sampling unit. So it is the first stage unit from which households are selected in a typical household survey. So typically in a PSU, you see like some 10 to 20 households in a PSU. It's like a small cluster of households, right? So usually they face the same price because a PSU in a rural setting will be typically a small village, or PSU in an urban setting will be usually an urban block where households tend to live together. So in a village, you can pretty much rest assured, you can assume that the villagers in the same village would by and large face the same prices. Similarly, households living in a cluster of urban location, an urban block, will all be facing by and large the same price, right? So we aggregate we take an average of the prices of all households in a given PSU or a given village, and assume that that is the price faced by all households in a PSU. I hope you understand what I'm trying to say. So instead of taking individual prices for individual households, and to alleviate the problem of not having prices for some households who are not consuming, we need to say that, yeah, these consumers are not consuming despite the fact that this is the average price prevailing for cigarette in that particular village. So we want to find an average price or average unit value of cigarette faced by all households within a PSU, and then assume that that is the price faced by every household within that PSU. So obviously, when the model is done, we will have prices varying only across PSUs, and there won't be any price variation within a PSU. And in fact, this is exactly what Deaton's model also assumes, right? So if you remember the second part of the Deaton's model, it assumes that the variability across the PSUs, right, across clusters, and that is what the Deaton's model exploits. So obviously, we don't want to see demand within a rural village being affected by price variation within the village, right? That is the idea. So, and this also solves actually one of the identification problem. You see, typically when you do a demand estimation, you see an endogeneity issue. You are familiar with the typical endogeneity problem in prices. Usually, the price endogeneity can result due to two reasons. One is an unobserved heterogeneity or simultaneity. Simultaneity is the one that we've often seen. It is essentially a joint determination of cigarette demand and price. The fact that we are not taking prices faced by individual households, but we are taking an aggregate of prices or an average of prices faced by all households within a PSU, we are addressing the problem of simultaneity, in fact. And this has been confirmed in some of the literature, even in the literature which has done studies of two-part model, estimated two-part model using GATS data, Global Adult Tobacco Survey data. They have come across this endogeneity issue, and they've suggested, this literature has actually suggested the use of an aggregate or an average price within a community or within a district or within a state as a solution to address simultaneity issues in the joint determination of cigarette demand and price. And then unobserved heterogeneity is another factor that can contribute to endogeneity of prices. And the unobserved heterogeneity is essentially the kind of differences that you see exist across different regions. For example, let's say, for example, in a country you have 4 different states, or four different districts, and suppose the anti-smoking sentiments differ substantially between different regions within a country. And then if you don't use anti-smoking sentiment as an explicit control variable on the right hand side, then the omission of that particular variable can cause endogeneity on prices, right? So this is the reason why we explicitly include some of these variables, like exposure to cigarette advertising or anti-smoking sentiments or access restrictions, etc., as different characteristics that might potentially differ households across different regions. So in the event that these variables are not able to fully explain some of these unobserved heterogeneities, that can be addressed by the use of regional dummies. And that is the reason why involve region dummies explicitly into the model, to capture some of this unobserved heterogeneity. So by including these regional dummies and these other regional level factors like exposure to cigarette advertising or anti-smoking sentiments, etc., we are able to address the potential endogeneity issues arising out of unobserved heterogeneity. And by using an aggregate or an average unit value or price for a given PSU, to an extent addresses the simultaneity issues that leads to endogeneity of price variable. So use of good control variables and region fixed effects, as well as the use of PSU level prices instead of an individual smoking price, will help address the issue of endogeneity in this model. That is the idea. So once you average the prices across the PSU, you essentially have the entire set of households, and you also have the price variable for the entire set of households. So you don't need to eliminate any observation at all from either part of the model, either from the first part or from the second part. I hope I have made sense of this discussion. If you have questions, please feel free to intervene in between. So how a typical 2-part model is implemented in Stata, I'm just walking through some Stata commands at its very basic. I will go through it in a Stata do file and do the exercise before you, then it will be much more clearer to you. So the example, Y is the number of cigarettes consumed, and YD is the dummy variable, taking the value 1 if Y is greater than 0 and 0 otherwise. So YD will have values 1 and 0. Log Y is the logarithm of Y if Y greater than 0. And we define a global macro in Stata, a global macro X, which is all the covariates like variable 1, variable 2, basically all these variables that we discussed here. They will all be the covariates. They are all defined in a macro called X. So why we define this macro? Coding becomes much easier. So in the part 1 of the model, we simply use a logit model, logit YD, where remember YD is the 1, 0 variable. It's a dummy variable representing your probability of smoking. YD $X. $X is a way to tell the Stata to list out all these covariates that are defined in the global macro X. So you can either use a logit model or you can use the probit YD $X. So it will execute the command YD on this set of covariates mentioned, defined in the global macro. In the second part of the model, we can use a regression model, which was traditionally used as regress Y $X if Y greater than 0. So remember, this regression is only for a subset of the sample for those households who are consuming. So only for consumers, so we define the regression is done only if Y is greater than 0. So regress is the command regress Y $X. And if you want to use the logarithmic transformed model of the OLS, you can simply use the regress ln y $x if y greater than 0. And now the last is the GLM, which is the preferred model. The command is GLM y $x if y greater than 0, and we specify the family as gamma and link function as log. And we add this robust option just in case, because we already saw that the GLM does not require assumption of homoscedasticity, but we are still adding a robust option just in case there is a heteroscedasticity. We can address those things with the robust option. In fact, instead of robust option in Stata, you can also use a cluster option. This is cluster level heteroscedasticity contributing to heteroscedasticity of errors. We can also use a cluster variable in there, and instead of the robust command, you can use robust cluster. And then once these models are done, after each stage, Stata allows you to use what is called a margin command to estimate the marginal effect and elasticities in each part separately. So after the first part and after the second part, you can use a margin command to not only to estimate the marginal effect of each of these covariates on the left-hand side outcome variable, but also to estimate the price elasticity in each of these parts separately. Now there is a two-part model package, 2PM package in Stata, which allows this estimation in a single short command, and that is called 2PM, TWOPM. It doesn't come as default installed in the Stata. You have to install it separately. You can use the SSC install 2PM command in Stata. You can simply write this command in the dialog command window in Stata and enter the command SSC install 2PM. It will install the 2PM package. It's a user written package developed in 2015, not very old. So the command will be, so in this 2PM package, once you install, both the first and second part can be modeled in one single shot. 2PM y $x, where y is the dependent variable. See here, this y here will consist of zeros and non-zeros. So it will basically be the number of packs of cigarettes consumed. It will be either 0, 1, 2, or anything. So any positive value, any non-negative values basically. So the y here will consist of the entire distribution. So you don't need the use of the yd or the dummy variable for the y in this particular model. You only need the y variable. Y $x, and the first part we are specifying, the first part is a logit model, and the second part is GLM with the family gamma and link log, and we again specify the VCE robust option. This will give you identical result as what you would get if you were to do this estimate in two different parts, as one logit model and one GLM model separately. So this gives you identical results as in the previous two-step implementation. It is the use of this 2PM package is useful in some sense, especially it's easy to conduct joint statistical test parameters from both the parts. If you were to do it in a two-step implementation as before, doing a joint statistical significance test will be more tedious. It's easy to recover overall predicted values of the dependent variable and marginal effects for the combined model. So you can get an overall prediction much easier using this 2PM package. So overall prediction, when I say it takes into account probability of consumption as well as the quantity of consumption. So whereas when you do a predict command after the if we were to do this two-step estimation, we have to first predict the probability in the first step, and then you predict the quantity of consumption in the second place, and then you have to multiply them manually to get the overall expected value of consumption, right? But 2PM will allow you to get it in one shot. That's advantage. It automatically computes the standard errors of predicted values and marginal effects and accounts for both parts of the model. So these are some of the advantages of using the 2PM package. But If we want to have separate estimates of elasticities, we need to use two-step implementation as we did before. Given that your interest is to focus on prevalence elasticity, you probably will get your answer even by doing the simple first part of the model. But it's good to have both. The GLM family modified park test that we already talked about, how that is implemented in Stata. The purpose here is to determine the relationship between raw scale mean and the variance function. So basically, you have to look at the relationship between expression of y given x and the variance of y given x. So use a GLM family test called modified park test with GLM here. So command is GLM y $x family gamma link log. So you basically issue the standard GLM command with the gamma and the log link, and then you predict the y hat. You predict the y hat with the option mu, which is basically predicting the y hat in raw scale. If you don't mention mu and simply issue the predict y hat, it will predict y hat comma xb, which is a linear prediction, and that will give you wrong results because it's a log link. Your y variable is in log basically. So you don't want an xp prediction, but you want a y hat predicted in raw scale. So predict y hat comma mu option, and then generate raw square. Basically, you're taking the square of the raw residuals. So the raw residuals are first computed y minus y hat. You take the square of that. That is the square of the raw scale residuals. And then you run a regression, again a GLM regression, GLM of this estimated raw square on y hat. Again, after specifying the same family and link functions. So the coefficient associated with the y hat will guide your selection of the family. If the lambda, which is the coefficient associated with y hat in this regression, we already discussed it, depending on whether it is 0, 1, 2, or 3, we will choose which family of distribution to be used in the GLM model. To test this coefficient for each of these values, we can do a statistical testing. So I'll show that in the Stata program. Then we go to the box-Cox regression, basically doing a link test. The purpose is to determine the relationship between the x beta and the e of y x. We basically we transform the y variable on the left-hand side using a power transformation, and use the command box-Cox. That is a particular command available in Stata. It comes as standard. Box-Cox y $x if y greater than 0. Remember, we are only doing a GLM link test, so this is only for the second part of the regression, second part of the model. So we specify it only for the cases where y greater than 0. Stata reports this lambda as /theta for the test, so you should be mindful of that. And then the link test the purpose is to test the linearity essentially. Estimate the GLM regression first. GLM y $x is the same GLM regression that we've been doing for the second part of the model. And then you predict Ly hat. It's a log y hat. So we are using the standard linear prediction. So xb is specified. And then we generate Ly hat square, which is the square of the previous predicted y hat. Predict the raw scale residuals and square them. So we predict the linear Ly hat, and here we predict the raw scale residuals using the mu prediction, predicting y hat in raw scale, and then take the square of that. And the regression is run on row 2 Ly hat and Ly hat square. So we want regression output from this regression. We are more interested in looking at the coefficient associated with the Ly hat square variable. We want that coefficient to be insignificant. If that variable is significant, it means some square of the xb, or some variables have to be specified in xb, or the specification is not right. It's not, the linear specification is not right. That is what it means. So you have to use, so the y hat square coefficient associated with y hat square has to be insignificant for the link test to pass. So test if the coefficient of Ly hat 2 is significant. Modified Hosmer-Limshaw test. The purpose is to check the fit of the model for any systematic bias. So you estimate again the standard GLM function we have been estimating for the second part. Predict log y hat using again linear prediction x beta, and predict y hat mu, which is predicting the y hat in raw scale, and then you generate the raw as a residual y minus y hat, which is essentially the raw scale residuals that are generated, and then you create 10 equal groups sorted by any specific x variable. Instead, we can use the xb itself, total predicted xb itself. So remember, Ly hat is the predicted xb. So we basically partition this Ly hat variable into 10 equal groups, 10 deciles after sorting them. So we use the xtile command, xtile, and you create a new variable group grp is equal to Ly hat if y greater than 0 and nq10, meaning we are telling Stata to create 10 different groups. And then we basically tab this group variable and generate set of 10 variables called decile 1, decile 2, decile 3 up to decile 10. That is what this command is doing. Tab grp generate deciles. So we'll end up with 10 decile variables, which are basically the deciles of the group variable that is created in the previous step. And now then the last step is to regress the raw residuals on all group variables, right? So regress raw on decile star, meaning on all decile variables we'll be regressing this raw residuals. And once that regression is done, we have to check the coefficient associated with each of the decile variables. So we want to test, the command is test palm decile 1 to decile 10. It basically tests that all these decile coefficients are equal to 0, or they're all different from each other. So those are the steps involved in some of the tests that we're going to implement. I'm going to discuss them now on Stata. I'm going to open my Stata program and walk you through each of these. Then you can actually simultaneously see the results appearing on the Stata window and see how things work out. So here is a list of references for you to read. Some of it I've already sent. I'm sure some of you have already read some of these references. But I suggest that you go through each of them before you do your exercise. It will give you a good idea of how and some of the other tests which I have not even mentioned in this discussion. You know, there are so many of them. We don't really need all of those tests available, but it's good to read some of these papers before you do the exercise. So here I will be using the particular database which Marco sent me a couple of days back, the HPS_Serbia0617.dta. I don't think all of you participating here would have access to this data except the team in Belgrade. It's so good, but you don't have to do it along with me. What I would do is I will open this do file which I have created for this purpose and load this particular data into my Stata. And I am going to close this this PPT and open my Stata window, and then I will start working through this data so that you can see everything. So, but before that, I think I'll take a 5 minutes break if you agree.
Can I just ask a question before we go for a short break? Just sort of like just maybe a summary from what I've got out of this, so that to make sure that actually maybe others do not agree or agree, or maybe they have similar questions. So my understanding is that the elasticities, the conditional elasticities then obtained in the second part of the model may be actually more precise than the elasticities obtained, conditional elasticity obtained by the even model. I mean, is it safe to say it like that? Given that the first part assumes this prevalence, predicts consumption based on that, and takes that information from the full sample to then estimate conditional elasticity.
But Violet, I should remember that the second part of the estimation here is totally independent of the first part.
So that's why obviously I misunderstood, because my understanding is that in the first part of the model, we use the information on the prevalence elasticity to predict consumption, and that, based on that information, we don't use the raw data on consumption from the household expenditure service, but we use actually predicted consumption based on the first part of the model.
No, that's not right.
And why not? I mean, why are we doing then the second part of the model? Why is then this information, the first part, useful? Besides getting on information on the prevalence elasticity.
First part of the model does not look at the quantity of consumption. It only looks at whether you smoke or not smoke. It does not bother how much you consume, right? So it is, first part is only a modeling of the probability of consumption, and second part is totally independent of the first part. That completely independent decisions. Once you made the choice to smoke, now second part asks how much you consume. So obviously,
all right. Yes, obviously you misunderstood what I was saying. So, but how do you link the first part? You said it's independent. Why are we doing the two steps if they have no relation to each other? So obviously, first part is relevant for the second part because the decision to smoke is made in the first part based on the price. So someone may smoke at the price, say A, but when price increases to B, then the decision to smoke decides not to smoke anymore, which is not included in the detent. Here we take into account that information, or not?
Yeah, but in the detents model, let's say if you were to do a detents model only with the consuming households, then it is the same thing. The second part of this model and the detents model is in essence the same. But of course, because of the differences in the method, the final output might differ, final elasticity estimate might differ. But in principle, the detents model, if you are using only consuming households to estimate the detents model, then it is the same as this particular model where you use the consuming households only in the second part.
So basically, there is no added value of doing the second part of the model.
For this exercise, yes. Yeah, I mean, if you have done a detents model, then there is no added value from the second part of this model. But then there is an added value. Where there is an added value, I'll tell you. If you want to do a prediction, okay, if you want to do a prediction based on both the parts, okay, you want to find the expected value of y given x, where y is the quantity of consumption and x is a set of covariates which are there in both the first part and the second part.
Okay.
So you want to do an expected value of y. Let's say you want to find the expected value of cigarettes consumed. Obviously, you want to find the probability of consumption multiplied by the expected quantity of consumption of those who consume. That is the actual expected value. Whereas if you don't do the first part, you only do the second part, and you find an expected value, then that expected value is somewhat it's not really correct, right? Because you're not really accounting for the fact that the probability of consumption is there. If you're only doing the second part, then you are in a way assuming that everybody is a consumer, because you are not accounting for the probability that there are only some people who are consuming. There is a possibility that some are not consuming. That is not accounted for when you do a detents model.
Okay.
So in that aspect, it is different from detents model. The fact that you are, while doing prediction, having the probability estimated from the second part is also factored in while you are doing the actual prediction for the entire households.
Okay.
Yeah, and if I may add to this, how I see it, and I think that actually using the detents model is slightly better than the second part of this model, because in the Deaton's model, we are actually acknowledging the fact that this is a unit value we are not talking about. And in this model, we are just taking the fact that we have unit value as a price.
Yeah.
And this is a huge assumption in a way.
Well, Marco, okay, I mean, you have a point there definitely, but in Deaton's model, you've seen that the quality shading in a unit value is not all that great. I mean, you will see that the quality elasticity is less than 0.1 or something, right? In most cases, in Deaton's model. So which means the quality aspect that is ideal, supposedly shading the unit values and stopping us from using unit values as prices themselves. The quality aspect is not, I mean, the magnitude wise, it is not so important. In fact, that is the reason why when you see Dayton uses the constraint, I mean, the symmetry constraint model in the end, he completely forgets the quality shading aspect completely from the model. He does not account for that when he is using the symmetry constraint estimate in the end. If you remember.
Yeah.
You see what I'm trying to say here?
More or less, but I'm just arguing that there is an additional value to the Deaton model compared to the second stage of this model. Just by the fact that in the initial estimates, we use this fact that we have unit values and the whole complicated procedure that we applied to arrive to price elasticities, because it actually explicitly takes into account quality, and this model does not. I'm just trying to differentiate between.
I agree. So far as the unit values differ from actual prices, if the variation or the difference is much higher in magnitude, Deaton's model becomes more and more important. You see, so the importance of Deaton's model comes in only when the magnitude of difference between unit value and price is larger.
Yes, I understand. But if you say it's about 0.1, the estimate of this coefficient in Deaton, it in a way corrects the estimated elasticity, maybe a little, but it corrects it, for the quality. So this is just, I'm not arguing that this is wrong. I'm just saying what's the added value of using the Deaton's model and
But if you want prevalence elasticity, you basically have to deal with the first part of this model at least.
Yes. No. This is completely clear. We cannot do anything with Deaton about the prevalence, and this is the main topic that we are investigating in this case.
But also remember, if you want to do a prediction on the total consumption, as a result, so let's say you want to do for our social scientists, we estimate these elasticities with the purpose of doing predictions for the policy making, right? For policymakers.
Yeah.
So if we want to, let me present to you a case why both these elasticities are necessary. Because suppose you want to see a reason why you want to see tomorrow the tax is increased on cigarettes. Now, increase of tax on cigarettes translates to increase in prices of cigarettes. So, when the price is increased on cigarettes by 10%, how much of that is going to change the consumption? Now, if you only have Deaton's model elasticity from in your hand, you're only answering the problem, the answer partially. The answer is only going to be partial. Why? Because the probability of consumption is not being taken into account. Now, in this model, when I am presenting both the prevalent probability elasticity of probability as well as elasticity in the intensive margin, what I'm doing is when I'm predicting the expected consumption as a result of change in price, what I'm doing is I am multiplying the probability of consumption into the mean consumption of those who are deciding to consume. So I'm multiplying both to get the actual increase in actual change in consumption as a result of price change. Whereas without the probability elasticity, or sorry, without the coefficient on the probability of consumption, I would not be able to tell you the exact change in consumption that is going to happen as a result of price change. Why? Because when the price change happens, there will be some people who are not consuming earlier may start consume now, or some people who are consuming earlier would stop consuming now.
Yes, clear. That's clear. Thank you.
Yeah.
So, Rijo, there is a question from Dragan. If you can just look at the box, in the chat box.
Okay, let me just bring my.
Does it mean that if we do not the first model, we cannot do the prediction aggregate level?
You mean in the Deaton's model?
No, here.
Sorry, I didn't see the question. If you
So
can repeat.
Does it mean that if we do not do the first model, meaning the first part of the model, we can do the prediction on aggregate level?
Does it mean that if you do not do first part, we cannot do the prediction on aggregate level? Yes, I mean we have to do the first part and get the elasticity of probability of consumption. That is the probability of consumption is a factor that goes into the prediction of aggregate mean change. Okay. If you remember, the expected value of y given x is the simple. This is a simple statistics, right? Expected value of y given x is nothing but probability of y greater than 0 into the expected value of y given x for y greater than 0. This is basic of statistics. So if you actually want to find the actual change in the expected value of y, you need to know both the probability as well as the expected value mean change for those with positive consumption.
Okay. Dragan, did Rijo answer your question?
So when I presented this in Stata, I show you how this prediction works from both the models and how in a two-part model how does it work. You will understand it better. I mean, I'll show you the predicted values and compare across different models.
Okay.
So here is my Stata screen, and I have my do file editor opened. So this is the do file I've created for this purpose. Is the do file the text on the do file readable for you guys? I've tried to make the font a little larger than normal, but still maybe it's not as big as you would see in a PPT.
Yeah, yes, it's fine. It's fine. Looks fine.
All right. So I actually made the text on both the do file and the window Stata window larger to make it more visible. Okay. So all right. So as you can see, the data used is the HPS_Serbia0617.dta, which Marco sent. I've not made any changes to that data. It is as it is. The key variables that are used for this analysis from the database is the MCE30, which is the total household expenditures in local currency unit, and NCIG, which is the number of cigarettes packs per household. I am not sure whether it was per month or week. Marco, can you remind me?
It's per month.
Okay, per month. All right. And then you have the unit value of cigarette, UV-SIG, and H size is the household size. And there is an ID COF, which is the dummy variable showing household coffee consumption. Dummy variable showing household coffee consumption. I believe in your Deaton model, was this coefficient significant, Marco?
We just, this just remained from the previous version of the do file where we attempted to estimate simultaneously the elasticities of cigarettes and coffee, and then to try for cross elasticities, but yeah, it just remained there without clear reason.
Yeah. So anyway, I've used that also as a dummy variable and touch, which turned out quite significant. So, and then we have mean edu, which is a mean education of household in years. And then there is a male ratio as another variable, which is basically the ratio of number of males to household size. And then there's another variable called adult ratio of the number of adults to household size. And then we have a dummy variable, a dummy indicator for the residence, whether you live in an urban or a rural area. And then there's a region dummy, which basically shows different regions in Serbia. I believe Belgrade, West, East, and the last one I forget. And then there is this house H type, which shows a variable indicating household type, basically their employment status and whether you are pensioner, etc. The four categories in that. And then we have a PSU variable, which is the primary sampling unit, a variable identifying the primary sampling unit or cluster. I hear a message that the audio is not visible. Is that correct?
I can hear you.
Okay. All right.
Does anyone else have problem? Yeah.
All right. Okay. All right. Okay. I think only one person has the problem. All right.
Besnik has a problem as well. Oh no, he's okay. Sorry.
Okay. Yeah. Okay. So all right, I'll proceed. So I just write this standard disclaimer here. The exercise done here is a demonstration for demonstration purposes only. The original analysis might need further checks and cleaning of data, additional variables as necessary before results can be finalized. So see, basically my purpose is to basically demonstrate how these models work and what kind of exercise you do, and all that we discussed so far. I just want to demonstrate here, but I've not really looked at whether some of these variables have outliers which needs to be removed, or which some additional variables needs to be included. Those things I have not checked at all, so please keep that in mind. And also this I believe, as I see, actually this data belongs to survey from different years. So the unit value that I'm using here is a variable. I don't know whether it is actually the real unit values already adjusted for inflation. Maybe Marco can say that.
Yes, it's adjusted for inflation.
Oh, okay, that's great. So which means I'm using the real unit values here.
Yes, this is a real unit value.
Okay, all right.
And all the expenditure variables are also real values.
Okay, that's great. So, but I'm not doing any year dummies or anything in the model. Those are things, because it's a multi-year database. Some of the time series properties this particular data might have, which might need addressing when you actually fit the final model. So with that disclaimer, let me start. So we basically start this Drupal with a clear command, which essentially clear the screen for us. So as you can see, there is nothing on the variable side. There's nothing here, and then I'm declaring the version of Stata. So I'm defining here a path to the directory where my data is stored. It is the path here, and then capture log close. Before opening any log file, this is a typical to issue this command, capture log close. And most of you are familiar with Stata, so I'm sure these are nothing new for you. And we start opening a log file, which will be stored in this particular path. So I'm using a global macro to define that path. So I don't need to repeat the path every time. I just need to declare the global macro, which is defined path. Path is a macro that is used here. And the data, this particular Serbia data that I'm using, is also stored in the same directory. I'm calling it in with this command. So as I go on, let me just run through this. I'm just running it still here. Okay, it's loaded here. You can see the data is all loaded here. On the right hand side, you have all these variables right here. I'm minimizing this variable window so that the result window is what you see and it's more visible, better. All right. So first, I just wanted to see the nature of this PSU variable. The primary sampling unit. So I use this command codebook PSU. It gives you certain information, like for example, there is 985 unique PSUs in this database, and of course that in this particular data, the same PSU number is given for multiple years. That is some anomaly I have observed. So I have to sort I'm basically summing the PSU by different years here. If I sum the PSU by different year, you will see that for this data runs from 2006. In 2006, there were so many 1248 PSUs in the year 2006, and then 1261 PSUs in the 2007 year. So similarly, the number of PSUs in each year remains more or less the same throughout all these years. There's not much significant difference, but only in 2013 there's a significant jump in the number of, by 2013 and 2014, a huge jump in the number of PSUs. I'm not sure why that is the reason, but anyway, that's material for us. So I just wanted to show how these PSUs are distributed across the different years. So as you can see, the values, obviously this value 1, which a PSU takes in a particular year, will be repeated every year. So our idea is to create a unique PSU ID for each year. So I'm creating two different variables. One is a household ID, which is formed by a group of year PSU and IDHH. IDHH is the household ID that is already given in the data. So by creating like this, I will have a unique household ID for each household distributed across the year and PSUs. And then I'm creating a, okay, let me also run this as I speak. Run this. There's one missing value generated. I think there's some one missing PSU observation or and then I have I'm creating a PSU ID so that it varies from year to year also. See now, as I showed earlier, you have the same PSU number repeating every year. So I don't want that happening. For me to have unique PSU IDs running through all the years, I'm creating a PSU ID variable with the command en PSU ID with the year and PSU grouping. So now if I code, for example, if I use the same code book PSU ID, sorry, PSU ID. Here I have 5,556 unique values. Okay. All right. So so I've created a unique PSU ID. So basically, these many 5,556 PSUs are there in all these years together in the data. So okay. Now I'm generating a price variable for each PSU and year separately, right? So I'm using the command psig, which is the price of cigarette, as the mean unit value by PSU ID, the PSU ID that I've created for each year. So when I run this command, it has created a new price variable, which is basically the proxy of a unit value as the proxy of price here, but by PSU ID. So for every PSU in every year, there will be a separate price, which is essentially the average of unit values faced by each of the households within those PSUs in every year. Okay. now look at this. When I generated that, there are around 2,195 missing values generated, which means those are the PSUs where there were no households with any positive consumption. So obviously, which means there were no unit values available in those PSUs to aggregate, right? So for such PSUs, I don't want to I don't want to ignore those data because it's huge. It's 2,195 missing values. It's not that many PSUs. It will be, you basically divide it by the average size of PSUs. Then you will see the number of PSUs where missing price information is generated. So instead of ignoring those PSUs, I basically attributed. I found the average unit values for each year and residence, like urban rural residents. I'll find average unit value and impute that to those missing PSUs where no price information or no buyers are available. You understand what I'm trying to say, right? So basically, I calculate when I calculated the average unit value or average prices for each PSUs, there were a couple of PSUs for whom there were no households reporting consumption. For those households, for those PSUs, I basically computed the average price prevailed in an urban area in that year, in the urban area in the country in that year, and assumed that as the price faced by all households in those PSUs where missing information is there. Okay, you can debate on whether this approach is good or bad, but I mean, you can make changes. I mean, you can, instead of doing it by year and urban, you can do it by year and region of the country, for example, so that it is more accurately represented. Or you can find some other ways to attribute or impute prices on these missing PSUs. That is welcome, but this is just for demonstration purposes. So here, for those missing PSUs where no households reported a consumption on cigarettes, we will assume that they face the same price as prevalent in the average price prevalent in the urban sector in a particular year. So that I will run here. Okay. So again, there's one missing value. So obviously now, if I sum PSIG, I have 59,859 observation. So the prices, the average price of a pack of cigarettes run from 31 local currency. I'm forgetting what's the local currency. Okay, what is the local currency?
Dinar.
Serbian dinar. Yeah.
Okay. So yeah, yes, dinar. RSD, right?
Yes.
Yeah. So it's 31.5 RSD minimum and 172.2 RSD maximum, with an average price of 84 RSD per pack of cigarettes. You must tell me whether it looks reasonable or not.
Marco, does it? I mean,
It
looks kind of low.
It looks reasonable given the fact that these are the prices from 2006.
Okay.
So because all the expenditure variables are deflated to 2006 values.
Yeah, that makes sense.
Okay. Okay. Yeah. Yeah. Great. Okay. So and then so I generated the average PSIG by year and urban, but I have to basically I have not imputed it. So for all the missing values where households were missing, households did not have any cigarette consumers, I have to attribute that and then impute that basically, and then drop the average PSIG that is generated. So sorry. So the actual summary will be this actually after imputation. So after imputing, the average price of a pack of cigarettes becomes 84. It remains pretty much the same. Doesn't differ much. Very slightly. Before the imputation, we had mean at 84.18, sorry, 118. Now we have 84.07. So very slight difference after imputing for those missing PSUs prices. All right. Now I'm generating a dummy variable for the cigarette consumption. So dsig is the variable name I've given. Generate dsig is equal to 0 if nsig is equal to 0, and replace dsig is equal to 1 if nsig not equal to 0. So I have a dummy variable generated. Now you can see some, sorry, if I do tab dsig, right? Okay. Okay. So this shows we have a total of 62,000 households for whom data are there in this, and then we have out of that only 24,000 are consuming, 24,000 something are consuming, and 37, more than 50% are not consuming any tobacco, sorry, any cigarette products, cigarettes. This is what the dummy variable tells us. And then I'm generating a dummy variable for the region. Tab region generate rdum. So it will take the values rdum. You can see on the right hand side, it will take values rdum, rdum2, rdum3, rdum4, like that. So 4 regions are there. You can actually see tab region. These are the regions we have: Belgrade, West, East, and this one. So 4 regional dummy variables have been generated. And now we also generate dummy variable for household employment type. I'm generating the variable htdum. So again, see, we have unemployed, pensioners, self-employed, and employed. And they were the household types available, and we have created 4 dummies representing those. Okay, so basically we're preparing the data for the analysis. And then we have the we have the mean education variable, mean edu. Okay. Edu. So this is the education variable tab. Okay. Yes, if you see this, when I do this tab edu, you know, this education variable is actually supposed to be in years, right? It's the number of years of education for an average, sorry, average number of years of education for a household. So I just want to round those into whole numbers, so that you know what we end up with rounded years actually. You know, instead of saying that 12.8 years or 12.9 years, that doesn't make much sense. So I just rounded them and created a new variable, generate educ. So now if I tab, I have education running from only 2 to 20 years. So I have people with the minimum 2 years of education, households with the minimum average 2 years education, up till households with average 20 years of education. So the data is, the variable is regenerated like that. And then I have to find a log of cigarette consumption, the number of cigarette. This is for using the logarithmic model, in the second part. So I'm creating the log cigarette for log nsig. So obviously, if you can see 37,697 missing values. Those are the guys who are, or households who are not consuming cigarettes at all. You see D6, tab D6, this is 37,697. That many are missing now when I create the log, because for the 0 log is not generated. All right, and then okay. Now let's just check the distribution of nsig. Okay. Before we go into the 2-part model, I'm using this histogram command to see the distribution of nsig. which is the consumption of cigarette. As you can see here, it is highly skewed. You have these are all zeros, those who are not consuming any cigarettes. So it's quite a skewed distribution you see there. But now let's do the same thing only for only for those reporting positive consumption. Okay, so this is the distribution of number of cigarettes consumed for those who consume cigarettes or those with positive consumption. Again, this is really not a normal distribution. It is skewed to the right. You can see a big tail over there. And then, okay, so obviously the distribution of NSIG, you can actually look at it. You can actually see the zero positive distribution. Look at the summary here. Look at the summary statistics. As you can see, the kurtosis here is 7.8, much higher than 3, which tells that we have a leptokurtic distribution for this NSIG variable. So definitely not a standard normal distribution that we have for this variable. So we need to see whether using a logarithm of NSIG is going to help, or obviously the standard regression is not going to help at all. So now, having created all these variables, let's now move into the two-part model. The first part, I'm defining the global macro X as PSIG MC30, which is the total household expenditure, household size, male ratio, adult ratio, education, region. And in the region, I'm telling Stata, I've incorporated this as a factor variable. So I'm keeping B1, which is first category, as the base category in the region, which is B1 actually is for Belgrade. So Belgrade will be the base region. And then for ID COF, again 0, meaning those who don't consume coffee, don't take coffee. Households who don't have coffee consumption will be the base category. Then IP3 H type, where the 3 belongs to employed households with households who are employed. In Stata, sometimes certain commands would not run if you explicitly define factor variables like this. So that is the reason why I have created another global macro X1, just in case we need it for some commands. So there, instead of specifying this region as a factor variable, for example, I have explicitly written region dummy 2 to 4 because 1 is a base category, so I'm omitting it. I can also write RDEM 1 to RDEM 4, in which case Stata will omit one region of its own choice, and we want a certain region as the base, so we want to explicitly mention that. So I'm writing RDEM 2 to RDEM 4 and ID COF and HTDUM 1 to HTDUM 3. In fact, this urban as the variable that I discussed in the beginning was included in this regression first, but I found that this particular urban variable was turning out insignificant in both the steps of the model. In the first part as well as the second part, it was coming out to be totally insignificant. So I just took that out of the model. So I have these many variables defined, global X and the global X1. I'm just defining them, executing it. Okay, that has defined those. And now the first part of the model is simply logit dsig $x. So basically, dsig is the probability of consumption, and X is the set of covariates that we have. So I run this model. You can see the model has been run, and This header all looks good. The LR chi-square statistic is significant here, and you can see the significance of individual coefficients. Most of them are quite significant, except this eastern region doesn't seem to have a significant impact on consumption, probability of consumption, but otherwise almost all the variables that we have included in here are significant. One, let's not get carried away with this result because you know that in typical regressions like this with really large number of observations, it's very hard to get a coefficient which is not significant. Most of the time, most coefficients become significant in large samples. So we have quite a substantial number of observations, 62,000. All right. Now, once we did this regression, we want to do a prediction. Okay. So we are predicting the probability of positive outcome. That is a default prediction. We use the option PR. So predict y hat p. Y hat p is the variable name that we are giving for the predicted variable. And we are telling Stata that we want the probability predicted. So PR option. Even if you don't mention this PR, it is fine because Stata by default assume PR for prediction when you are doing the prediction after logic or probability regressions. So we run this command, predict. Three missing values are there. Now you just summarize this predicted value with the dsig, which is the actual dummy variable for the consumption, whether to consume cigarette or not. So you can simply summarize both of them together and see how close the prediction is. Okay, either this many observation in the predicted and the three missing observation. As you can see, the predicted mean is very close to each other. 39.25 is almost up to 4 decimal points. The prediction is accurate. To do the elasticities, so I'm just leaving this y hat p out there for future use. When I do the two-part model, I will show you how this predicted values from the first stage becomes useful. So I'm leaving that y hat p behind. And now we are estimating elasticities. Stata has this beautiful margin command, which allows you to estimate, changes, marginal changes or elasticities depending on what you specify in the option. You can estimate either price elasticities or you can estimate marginal changes, etc. So here, see for example, to get the elasticities, we need to use the margin command. I'm estimating the elasticity for price elasticity here. So I use the option EYEX. That is the margin command because we are using EYEX for elasticity because we are already having a logit model. So we are using EYEX. The elasticity will be displayed along with its probabilities and confidence intervals and standard errors. We see the elasticity as minus 0.398. That's the elasticity. So now here, we can also do this elasticity for both price elasticity and income elasticity or expenditure elasticity together if you want. So that gives you a negative 0.39 negative price elasticity as negative standard, and income elasticity or the expenditure elasticity, if you may, as 0.26. So these are all elasticities, but remember, these are elasticities meaning a percentage change in the probability of cigarette consumption due to a percentage change in price or income. So this elasticity is telling you the percentage change in the probability of cigarette consumption. Okay, it is not telling you a percentage change in the quantity of consumption. So this is not the typical elasticity. Now, if you want, you can compute these elasticities these elasticities are computed at the average. Even Deaton's model you estimate, for example, the elasticity that you get is at the average value of the X variable that you, if you're looking at the elasticity for the price variable, it will compute the elasticity normally at the average value of the price variable. But as you know, the elasticity can differ across different values of price, right? Yes, a standard demand curve, the elasticity at every point of the demand curve is different, right? So you can look at that. For example, let's say I want to look at elasticity at different points on the demand curve here. Say I have my P6, for example. Let's say I see summarized P6. I have my price of cigarettes ranging from 31 to 172 RSP. So I want to see the price elasticity from price 30 all the way to price 180 with the intervals of a gap of 20 RSD each. So I specify it like this. Margin EYEX P6 at value of P6 equal to 30 to 180 with the intervals of 20 each, right? So if I estimate that, it will give me the value of elasticity at different price points if you want. So it takes some time, yeah. So it has given, as you can see, 1, 2, 3 up to 8. Tell you 1 means 30, 2 is 50, 3 is 70. At the price 150, it's 7. Okay, so as you can see, the elasticity is it becomes larger and larger as you move to higher prices. That is common sense, right? So on the downward sloping demand curve, you will see higher price elasticity as you go up the demand curve with higher prices. So in fact, you can use this margins plot command. There's something called margins plot. When you use margin to estimate the predicted margins like this, you can use the margins plot command to neatly present them on a graph. So you can see here, as the price of the cigarette increase, the elasticity also keeps increasing. It becomes more elastic as the price of the cigarette increase. So this is just for fun. I presented it here. Anyway, so the margins, I just wanted to introduce this margins plot command as well as the margins command to you. It will be useful. Now, you can actually look at the income elasticity this way. You can look at elasticity for other variables like this. So you can actually see the elasticity for by controlling at the value of, say, urban, rural, or depending on like household size or anything that you want to think of. But now, with the logistic model like this, there is also a concept called semi-elasticity, which is actually looking at a percentage change in probability of cigarette consumption for a unit change in price instead of a percentage change in price. Okay, so in that case, we issue the command margins EYDX instead of EYEX. We measure EYDX for P6. This actually gives me the percentage change in probability for a unit change in price. Whereas earlier elasticity was giving you the percentage change in probability for a percentage change in price, right? So this is depending on what kind of interpretation you want to present. The margin actually gives you this kind of flexibility. See, for example, here that I can also use DYDX, meaning I can see the change in probability of cigarette consumption for a regular coffee user, for example. Okay, I want to use that margins here, and I use the DYDX command. It says the coefficient is 0.03, so it means on average the households who spend on coffee have 3% higher probability of smoking. So this interpretation becomes very straightforward with margins command, right? But we could not have interpreted it like that from the raw output. Okay, from the raw output, if you see, where is this is a coefficient 0.153. It only shows that the log consumption, the probability goes up as if a household is a coffee consumer, right? But it doesn't give you better, more intuitive explanations. But these margin commands and using different options like dy, dx, etc., gives you much more intuitive explanations. So here it is so much more intuitive to say that a household who spend money on coffee, consume coffee, has 3% higher chance of consuming cigarettes. That is a much more meaningful way to explain to a policymaker, for example. All right. So, and you can see similar things for household size if you want to look at. Yeah, I want to see how the probability of consumption differs for people from different household size. So I look at household size from 2 to 20 with increments of 2 household members each. As you can see here, the probability of consumption increases for every new household, for every member that is added to the household. If I wrote the margin plot command here, comes easier. Okay. See here, as the household size increase, the probability of consuming cigarettes increase, right? So every increase of household member, there is an increment in the probability. Okay, added probability. I mean, these are only showing the additional probability, and that is why it's showing an decrease here. But if you see it, look at it cumulatively, you see that for every additional member that is added to the household, there's an increase in probability of consumption, probability of consumption of cigarettes. All right.
Just if I may interrupt, I'm sorry. I'm just not convinced that maybe using this ID coffee variable is maybe right, because we face an endogeneity issue. So we don't know whether a person who, is the consumption of coffee affecting the consumption of cigarettes, or is it the other way around? So maybe because this is not a crucial, just for everybody to have this just a thought. Sorry.
That's a good point. Yeah, I mean, that probability is there. You don't know the causation in which way it's really going. Yeah, you're right. All right. So yeah. So now we move to the second part. The second part, we can either do a simple OLS for those households with NSIG greater than 0. So I do a regress command, regress NSIG on X. It gives me the result for only those households who are consuming cigarettes. So as you can see, most of the variables turned out significant. So we have statistic is significant. Of course, we have a very low R square, meaning there could be many other variables which we are probably omitting. The predictive power is pretty low. Anyway, but let's predict the y hat here. I'm predicting an in-sample prediction, meaning only using those samples that is used for the analysis. So predict y hat. So it's a raw y hat that is predicted. So this many missing values, obviously, because we did the regression only for NSIG positive cases. Summarize y hat and NSIG to see how the accuracy of prediction is pretty fine. The predicted y hat and the average NSIG in the raw data, they seem pretty close. Here again, you can do elasticity using the same EY-EX option in margins. So as you can see, this is a conditional elasticity, which is coming out to be minus 0.488. That is the conditional or elasticity at the intensive margin. And the expenditure elasticity is coming out to be 0.27. So that is the elasticity. So now we got elasticity both places in the first part and the second part. But second part, we said oilless may not be an attractive option. So people use logarithmic transformed variable instead of using the cigarette variable in its raw scale. So we use the regression in with the ln sig variable, which is the log transformed variable for the cigarette n sig. So I can run this command here. It runs the model, and I predict ly hat. I'm using the L here to denote that it is the prediction from this logarithmic model. So ly hat. So now this ly hat is obviously, as we already discussed, because it's ly hat, right? We need to get the actual y hat in its raw form, right? So we need retransformation. Okay. Now the retransformation can be done either assuming that there is normality, or we can use the Duvan's smearing estimate. Okay. So if you are assuming normality, assumption, I can generate the y hat in its raw form, or the raw y hat assuming normality. So I put the subscript n here as exponential of ly hat. So basically ly hat, exponential of ly hat becomes y hat, but I'm also adjusting it for normality. So adding 0.5 into RMS root mean square error square to that, so that we get raw scale y hat, which is transformed y hat under normality assumption. If we transform using Duvan's smearing estimator, we have to see Duvan's smearing estimator first. For that, we first predict the residuals from this regression, basically predict R. When I mention the option R here, it means the residuals are being predicted instead of linear prediction XB. So predict R, and the smearing factor for Duvan is estimated as the mean of exponential R, right? If you remember the smearing factor, two-part model Duvan smearing. See, average of the exponentiated residuals is the Duvan smear. So we are exponentiating the residuals and taking the mean of that. Okay. So the D smear, the exponentiating R first and then taking a mean of that. So D smear is being created. So now you create the raw y hat is being predicted with after exponentiating the ly hat, you are multiplying it with the D smear that is generated. That is how we are adjusting for the bias that we discussed. We are smearing the adjustment here. So we have y hat D. So you can see here after smearing estimated, you can see a histogram of this estimated y hats imposing the normal distribution around it. It looks reasonably okay, but it's going outside here a bit, right? There's a tail also here, you can see a little bit. So we haven't tested whether the residuals have heteroscedasticity or anything, because we're not really going to do with this model. We're actually going to GLM. So I'm dropping this ly hat R and D smear. We don't need them anymore, but I'm retaining y hat D and y hat N, etc. from the previous model for future purposes. So see, what I'm retaining is raw y hat D, which are correctly retransformed, and then we have the y hat N, which is retransformed using normality assumption, and then I'm retaining the original y hat, which was predicted from the oilless model without doing any retransformation. Okay. So all the three y hats are retained. So now I can do the elasticity on this model also, and if you want elasticity percentage change in consumption due to percentage change in price, see here, because it is a log transformed model, we are trying to do the elasticity. The log y, the left hand side variable is already log y. So to get the elasticity, we don't use the EY/EX. Instead, we use DY/EX. And this is because we are already having a log term on the left hand side. So you see, elasticity is basically derivative of log y with respect to derivative of log x, right? That's elasticity, right? So we already have log y on the left hand side. We only use the dy here instead of ey. So here, if I use the margin, it will give me the elasticity. It's 0.49, whereas from the previous Euler's model, we had the elasticity estimated as 0.44 or something like this. It was 0.39. Yeah. Yeah. That's 0.39. All right. So slight difference, but it's pretty close. Okay. All right. And again, you can see margins dy ex at different price points. The margins plot, I'm not redoing those here. You can also estimate the income elasticity here if you want to do them separately or do them together. So conditional price elasticity or the elasticity, price elasticity at the intensive margin and the income elasticity at the intensive margin. Right. So now let's go to the GLM, which is the preferred model. And again, remember, this GLM is done on positive outcomes only. That is the second part. Okay. So the standard command is to use GLM nsig $x if nsig is greater than 0, meaning we are telling Stata to do this GLM only for positive consumption. We're using family gamma and log link using the option robust just in case. So it's running the model fine. It ran the model. It displays all kind of statistics. So you can see this is the variance function is shown here. It's u square here. The link function is the log. As you can see, there's some AIC, BIC. These are all goodness of fit statistics that is typically shown. As again, almost all the variables are quite statistically significant. Do a prediction now. Again, see here, because it's a log link function that we've used. When we predict standard linear prediction, what we get is only Ly hat, right? So I predict Ly hat xb. Oh, sorry, that is already there. Okay, let me not predict that. It's not required now. So I had to drop that earlier one. Drop Ly hat. So the earlier Ly hat was dropped. I had to do this. I didn't drop it. Ly hat is already dropped, so we just want to drop the R and this mirror. Okay. That part was not executed. All right. So now I predict Ly hat xb. Predicting the linear is the linear prediction, and this is the raw prediction. Ly hat mu option. So this will basically predict the expected value of y, or the y in raw scale. It is nothing but the exponential of Ly hat. Okay. So I'm predicting y hat underscore g. G is written here to denote that it is y hat predicted from the GLM model. So I'm predicting y hat underscore g mu, and you should know that this y hat underscore g is basically equal to the exponential of this Ly hat that is predicted here. So now let's just summarize all the y hats that are predicted from different models for n6 greater than 0. So we have the first y hat predicted from the standard Euler's model without doing any corrections. We had y hat n, which is retransformed using normality assumption, and this y hat d is the retransformed prediction using these Duvan's smear correction, and this y hat g is from the GLM model, and this is the actual mean for the n-sig for cases where n-sig is positive, meaning more than 0. But from a cursory look at it, we would assume that the original Euler's model's prediction is coming much closer to the actual n-sig values mean compared to any other y hats that we have predicted. The second closer is obviously the y hat g from the GLM model. Okay, so that is what it is. But this doesn't mean that Euler's is necessarily a superior alternative. Obviously, you know that Euler's gives the best unbiased estimator, so it's a more efficient estimator. But that doesn't mean it's consistent. All right. So now there is a single short command. Let me just quickly show you the margins command for estimating elasticity for GLM. It's again the same EY-EX. Margin EY-EX for P-sig price, it is showing elasticity of minus 0.45. It's pretty close to the previous elasticities we got, 0.44, I believe it was. Okay, it's 0.45 now. You can also estimate the income elasticity here similarly, both income and price elasticity. It will show you minus 0.45 and 0.29, positive 0.29 as increments. These are both conditional elasticities or elasticities at the intensive margin. Okay. Now, a single short command to do all this using the 2PM package. You first have to do this SSD installed 2PM. Okay. Since I have already installed it, I just have to issue this replace command. So it is checking whether it is already installed. If it is already installed, it won't install. Since I have specified the replace option, it will probably go ahead and install it anyway. But you have to do it before you're able to run this command. Install. Let me paste that here. Okay. All right. So the 2PM command is simply the syntax is 2PM nsig $x, and the first part is logit. Second part is the standard GLM with the family gamma and a link log with the robust options specified. Okay. So we estimate that 2PM. You see here, it's been estimated. Just for the comparison, I'll do the GLM alone for the second part. Okay, you can see how close, how identical the results are. For example, this is the 2PM command. This is the logit part, and below is the GLM part. For the GLM part, you see the coefficient associated with P-sig is this minus 0.0055712. And in the GLM command again, it's the identical coefficient. Coefficient is identical, right? So make it easy. Just look at the constant, 3.18776. 3.18776. So these are identical results. Now, if you do the logit, logit nsig $x, it will give you estimates identical to the top part of the 2pm command. See, for example, constant here is minus 1.285 for the 2pm model. For the logit part, can you see here? It's minus 1.285. So it's identical. So it is just as doing two independent two-step estimations, right? You do the logit model separately, do the GLM separately for the second part. It's identical. Instead, you can simply do a 2pm command to do the estimates simultaneously. So the advantage is in terms of the prediction. Okay. So, for example, here, so here again, I'm using predict here. Predict y hat TPM. Okay. I'm predicting the y hat. Obviously, this is a prediction which takes into account the probability part as well as the quantity of consumption second part. Okay. Now, how do I compare this prediction with the previous two-step estimation? For that, I need to be able to generate a new y hat sum, which is the product of y hat p and y hat g, wherein y hat p was the predicted probabilities from the first part of the logit model, which we have already done, and y hat g is the predicted probabilities or the raw scale prediction for the second part of the GLM model. Okay, for the GLM model, we made a prediction for y hat, which was stored as y hat g, and for the logit model, we had predicted and stored the result as y hat p. Now, in the presentation, if you remember, I have the expected value of y calculated as yes. See, the probability of y greater than 0 into the expected value of y given y greater than 0. That was the overall mean that we want to predict, right? That is exactly what is done here. So the total y hat is the product of the probability from the first part into the mean value, the expected value of the mean from the second part of the model. So I'm defining those y hat sum there. Okay, so new variable y hat sum is generated. Now let me compare this y hat sum with the y hat TPM, which is the predicted value of y hat after doing the single shot command. Okay, so I'm just summing it up, summing both the y hat TPM and y hat sum, which is the product of both the parts together. As you can see, those results, why it is why it's not the same. The result has to be identical. Something going on. Go back and check. Drop or y hat star. Y hat. I'm dropping all the predictions so far. Logit DCX and predict y hat p. Oh, this is y hat p that I should be using. I think I made that mistake. So y hat p is the predicted raw predicted value from the first part, and the second part we have GLM with the family link. I'm running it and predicting the Ly hat G. So we have raw Y hat G and Y hat P now. So now I'm doing the single shot command 2 p.m. I'm predicting the Y hat T p.m. Y hat T p.m. And I have Y hat sum as Y hat P into Y hat G. Is correct? Okay. Let's check now. Okay, correct. There was some mistake somewhere. Now you can see both the Y hat TPM and Y hat sum have as identical numbers. You see, this is the advantage of doing a 2 p.m. two-part model in a single shot. So the idea here is that if you were to only estimate a conditional elasticity, for example, the predicted mean, from let's say from the predicted mean would be, for example, with this you also add Y hat G. That is the predicted mean for the second part of the model alone. Okay. See, the predicted mean varies significantly for if you were to do only the second part. In fact, for the second part of the model, this should run like this. If n6 greater than 0. Okay. So 34 is the average consumption, or the number of packs, average number of packs consumed in a month. If you were the predicted number of packs consumed in a month, if you were to use only the second part of the model, would have been 34.10. But when you use both parts of the model, both the first probability part and the expected part in the second, the actual predicted consumption for the entire sample, for the whole households in the survey, becomes only 13.42. So these are two different means we are arriving at, depending on whether you take into account the probability part in the first part of the model or not. Now, do you see the merit of doing both the parts separately or together as in 2 p.m. command, or ignoring the probability part and only doing the conditional part and estimating the conditional mean? Do you see the difference and the merits here? I'm just asking for some feedback.
Yes, but this means actually that also those in the data who have zero consumption will have a positive predicted values of consumption.
Yes.
Which of course depend on their probability to have these expenditure as well. Is this a little bit strange or a little bit misleading in a sense that we are artificially imputing these values to persons who have actually no consumption?
See, it is about, from a country's point of view. For example, let's say from a macro perspective, if a tax policy is designed, right, and you want to increase the price and you want to see how the average consumption in the country change, are you going to look at the consumption of only those households who are currently consuming, or do you expect that your price policies or tax policies could also impact those who are not consuming at the moment? Some of them could start consuming, or some of them could exit from consumption. Then if you think so, then don't you think both the households should be included in any kind of predictions?
No, I agree completely with you that we need to take both things into account. I'm just wondering, and yeah, I completely, I'm aware that my knowledge about this is limited. Whether the fact that we actually are going to impute some values of expenditure to the households which do not have expenditure at the moment. So practically, I'm just wondering, we are not doing any reform at this point, and we are not looking at any reform at this point, but we are just asking, okay, so yes, so households which have zeros in the database, we are imputing some expenditures to them. So yeah, but I guess that this is the minor point. We can discuss this later, not to you know, overextend this. I think that the main thing that we are here trying to do is estimate these elasticities. So
Yeah.
And we can further discuss this issue.
So obviously both have different purposes. So probably, you know, what model to choose here would probably depend on the kind of purpose that you have in terms of devising policies, and you know, the what kind of predictions that you're looking at. If you really want to look at the prediction from the point of view of the whole country and including all households, then you know, any averages should reflect everybody in the country, right? See, for example, when a country list tells you, okay, your per capita income, average per capita income in the country includes every households. You know, there will be some with a very large income, and there will be some with a very low income, right? Similarly, when government says, yeah, this is the average expenditure on, or the average on average, 20% of the budget is spent on food in Serbia by households. Does it mean everybody is spending 20%? Or let's say on average 5% is spent on consuming tobacco in a country. There may be a large number of households who don't spend anything on tobacco. Still, the 5% applies to everybody, right? So it is something like that. When you talk from a country's perspective, macro perspective, the averages are distributed. The denominator becomes the whole population instead of those with only positive consumption. That is the idea behind this kind of a model. Of course, both has its merits and demerit, and you can decide which one to use depending on the specific purpose that you have in mind.
So that was my actually kind of observation, comment, when before we actually moved on, before we went on a break. It was that in a way, for the purpose of informing the policy, these estimates are a little bit more precise than the one that we provide by doing this model, because in this way we take into account all population. We look at the impact basically in both ways. So instead of only focusing on forgetting the past, where actually certain price already has incentivized certain consumers to drop out of the consuming population, so not there anymore, we now take into account everybody.
Yes.
So this was what I was really, it wasn't really completely clear with in my head as well before we went through the steps of the Stata, but it looks to me that this, at least for the purpose of policy making, this is more precise and specific.
So from a point of view of prediction, this gives a more realistic prediction for the whole population. But if you are only interested in a prediction for consumers, I mean only for you're interested in a prediction only for those consuming households, then of course you only need a second part of the model.
Okay.
But from a policy perspective, if you want to do a prediction for the whole country, both intensive and extensive margin elasticities are useful.
Okay.
And that is the reason why we go for a two-part model.
Okay. Thank you.
Yeah. All right. So yeah. So that okay. So similarly here, when you do the price elasticity here for the two-part model, okay. So the single short command, I use the two-part command once again. So two-part command here. Okay. Okay. And I can estimate price elasticities combined, this margins EY EX here. Okay, E by X. See what the price elasticity I get is 0.866. That is the total price elasticity for taking into account both the part of the model. Whereas when we separately estimated price elasticity for participation and price elasticity for consumption, in the second part, we had values like, for example, I'm forgetting, let me just do it once again. GLM price elasticity was the margin C by X. Price elasticity for GLM model is 0.4536. Let me just put it aside on an Excel sheet. Okay. So I have this is the elasticity from GLM, second part, and first part, logistic. I need to do this thing again. For the logit model, first part, logit, and I'm estimating elasticity by X. We have elasticity minus 0.39. And the two-part model, we have the elasticity already worked out as 0.861. This is from the two-part model, 2 p.m. Okay, so if we sum these elasticities from the independent step by step, it's 0.85, whereas from the single shot command we get an elasticity of 0.86. So they're pretty close, right? So in other words, this is the total elasticity from the elasticity that is generated from the 2 p.m. model in a single shot command is what you would ideally use for policy purposes. Whereas and you can separately see or this value or this value. Whereas from the Deaton's model, you would have got an elasticity probably closer to the second part of this model if you only used the consuming households. You might have your elasticity may be compared with the elasticity of the second part of this the two-step process. But remember, these elasticities are really, strictly speaking, not comparable because they are totally using completely different methods. While the Deaton's model is correcting for unit values and also correcting for measurement errors, etc., it is theoretically more superior, I would say. If your interest is only to look at the second part. But here, if for policy purposes, it helps to have a total elasticity which takes into account both the probability of consumption and also the elasticity in the intensive margin. So both elasticities, you get a total elasticity of 0.85. So I don't know about Marco. Do you remember what the elasticity you had got from Deaton's model? I mean, I'm not saying these models are correct.
Yeah, the latest estimate that we have is about, if we use the whole data, it's 0.395.
395.
Yeah.
Okay. So that's coming closer to the second part of this elasticity estimated here, right?
Yes, and it's actually the one only estimated on the intensive margin. So we exclude even in the budget share equation, we exclude those who have 0 unit values.
Yeah. So obviously the model specification, particular specification we have used in this exercise and the one you used may be a little bit different, but that apart, I see that the elasticity on the intensive margin elasticity estimated in this two-part model is not so very different from what you got from the D-TENS model.
Right? Yeah, I would agree.
Yeah, and that's actually a good thing, right? Because you can say that, hey, no matter what method we use, whether we use the D-TENS method or we use some other method, we are coming up with elasticities which are not so drastically different from each other. That's a really good thing in my opinion. From a
No. This really sounds promising, especially given the fact that in the D-TENS model we perform this kind of we exclude the extreme values and so on. So this estimate is, I think that I attempted also like an estimate without excluding extreme values, and I think it's about 0.42. So it's even closer. And I'm feeling that this one is going to be even closer when we deal with the extreme values issues and so on.
Yeah, so maybe you refine this data and do this 2PM model on your data on a refined, clean the data. Maybe these elasticity numbers becomes even more closer. That
I can expect that.
Yeah, that's great. So so that's it with the elasticity estimation. In fact, we can do the total elasticity from using this margin commands. When you apply the margin commands, make a special note of the option EY or E or D that you are specifying. That's very important. Depending on the model specification, the EY and D, E and D will change. So please take care of that. So now the elasticity estimation is over. Now let's move on to some model diagnosis here. It's 10 o'clock now. Yeah. Already. Okay. So let me do this. I just need to run this all over again once so that you don't miss out. Just do it once. I see that there are certain commands I have not really explained in between, but they're not very important. But when I sent you the do file and the certain lines of commands which I've omitted from explaining, but I've added some comments on the right side, and you can see, you can run each line by line and see the results that is appearing on the screen, and then see what is going on. See, for example, margins dy dx star. Um, if you run that, it will give you the conventional interpretation showing incremental effects. See, typically when you do these GLM functions, GLM or even logit regressions, the coefficients that is reported are not really readily interpretable in a sensible manner. I mean, it doesn't give you very good intuitive explanation, and that is the reason why we use margin commands. Once the margin is used effectively, we can transform these coefficients into more intuitively explainable ways, right? That is the reason why we use these margins. All right. So okay. So here, first we're doing the GLM link test, which is the box-cox test. For this, you simply need to do this command box-cox nsig $x1 if nsig. So let's see where the box-cox command here is. Box-cox. Okay. So here's the box-cox. So you know how the box-cox will essentially transform the y variable into some power form with the lambda, and our objective is to find the value of the lambda to see which log function we can attribute. So box-cox nsig, it's run. No, it's not run. Okay. Box-cox. See, I'm running the box-cox on x1 macro instead of x. Why? Because if you run it on x, it will give you an error saying factor variable operators not allowed. So you have to use the global x1 instead of x. But the results are identical anyway. Doesn't matter. So the result has come for the box-cox. What we are interested is this theta here. Okay. So the theta value is what we is of our interest. So it is taking the value 0.42. Okay. So now look at this table here. If the theta or the lambda here is 0, it's a log function, log link. If it's 0.5, it is actually a square root link. If it's 1, it's an identity or linear link, right? So it appears that a 0.5 is so much more closer to the theta value we got, 0.2, 0.4. So the box-cox regression is suggesting that we use a square root link instead of a log link in the GLM specification. But please remember that that is box-cox results can be misleading sometimes if the errors are non-normal and heteroscedastic and all that. Sometimes box-cox results, and some people actually don't bother with the box-cox, and they say that your model selection should ideally be led by your own intuition and how you think the data is, or the data generating process. And this is just like this box-cox is usually just a very automated data-driven mechanism which suggests you. But yeah, we can do the GLM with the log instead of log link. You can write the power. You can say instead of log, you can say power 0.5, and then it will run the model without any problem. So that is one way of testing the link function in the GLM. To test the family distribution family, we use a modified park test. For that, we run the GLM model first. We run the GLM model, and then we predict the log y hats using the linear combination prediction, linear prediction. Y hat is already defined. Okay. So I predict the Ly hat. Predict Ly hat. Predict y hat g, which is basically the predicted y's in its row scale. The row scale, it is essentially nothing but the expected exponentiated value of this Ly hat, which is already predicted. Then I'm creating the row residual square, which is the n sig, which is the actual y variable, the row y variable, minus the row predicted y variable, the predicted y hat variable, and the square of that is defined as the residual square, the row residual square. You can see here the modified park test is done like that. The y minus y hat square, and take the log of that, right? So row y w square, and then you do a regression of this row residual square on Ly hat using the same GLM command. You do that, and what we're interested in is the coefficient on Ly hat. Coefficient on Ly hat is 2.0, 2.06. You see here, if the lambda is 2, it means it's a gamma distribution. So from the modified park test, it shows that the coefficient 2, it's not exactly 2, but we can test that actually. So you can, there's a test to see whether Ly hat is equal to 0 or Ly hat is equal to 1 or 2 or 3. Okay, you can do each of these tests, you can run it one after the other. So you can see here, if you test it for Ly hat is equal to 0, it's rejected. Ly hat is equal to 1 is rejected. Ly hat is equal to 2 is not rejected. So which means the gamma family is the preferred family distribution. So we want the test command with it should not reject the hypothesis here that Ly hat is equal to 2. All right. So we are good with the modified park test and its suggestion that the gamma is the right family distribution to use. GLM testing for nonlinearities, it's a link test. For that, first we have to generate the Ly hat square. See, essentially for the link test, as you already saw here, it tests whether the coefficient of y hat square is significantly different from 0. We want to see the coefficient of y hat square from the regression model. The model is specified correctly, y hat square should have no exponential power. So we define the y hat square first, Ly hat square. Okay, and we do a GLM regression of row square on the Ly hat and Ly hat square, and we have to basically look at the coefficient associated with Ly hat square, and it should be statistically insignificant. You can see here Ly hat square. You can ignore this coefficient. Just have to focus on y hat square coefficient. As you can see here, this is the right result we want. It is not rejected. The null hypothesis is that the Ly hat square is significantly different from 0, but it is not being able to reject that. So yes, yeah. So the link test is passed here. The null hypothesis that the model is linear, the coefficient on y hat should be statistically insignificant.
And if this part were to be significant, what do we do?
If this were to be significant, that means the model is not specified correctly. It could be because you have omitted some variables, or it could be because your model is actually not linear. It could be like, for example, your age variable might have a square term of square of the age variable is also significant, or it is possible that there is some interaction that you are missing. It is basically trial and error. You have to.
Okay.
I'm fortunate that it worked better with this now, but that doesn't mean it should work with every other data for sure.
Yeah. No problem. But the idea is that then we can toy around a little bit with the specification, maybe include some squares and so on. So yeah.
Yes, squares or maybe interactions. Many times when this link test fail, interaction between a dummy variable and a continuous variable, some sensible interaction sometimes make it right.
Okay.
This all, this basically trial and error is what you have to resort to.
Yeah. Okay. So thank you.
So that is the link test. So I'm again dropping this right here. Now, testing the deviance residuals for goodness of fit. Actually, in this book by McCullough and Nelder, they recommend this deviance residual test as having the best properties for estimating the goodness of fit of GLM. Okay, this is written in their book, and it is also suggested in this recent book by Jones 2013, Applied Health Economics, Routledge 2013. Also recommends this deviance residuals as a good test for looking at the goodness of fit of the model. So for doing that, you just simply need to predict the residuals, a deviance residual. The Stata actually straight away gives you an option to predict the deviance residual if you mention the option deviance. Okay, so you say predict res underscore d to denote that it is a deviance residual with the option deviance. Okay, so that is done here. By for not found. For doesn't matter. Let me run this model once again. Oh, okay. Why this is not doing it is because I have run the GLM